Okay. Ma'am, sir, ladies and gentlemen, thank you for coming to the first presentation session of this year's project series here at Physics and Engineering departments. My name is Major Gavin Chase. I'm an instructor in this department, and I'll be facilitating as the chair for this session. We're about to do some awesome talks about a wide range of really interesting topics. Before we begin, I would like to remind everyone of a few things. Yeah, please come in. You're more than welcome. Keep coming. You're welcome. I'll remind everyone of a few things before we get started. First, I ask you just be respectful of the cadets who are giving their presentations. Specifically, make sure your devices are silenced. And I would ask that you just be mindful of the camera. There are some who couldn't be with us today who are joining us virtually. So just be aware that we are broadcasting live this entire session. Second, the talks will be about 10 minutes, okay? So Captain Caboose in the back will give you a signal when you're about halfway through your time. I ask you to hold your questions to the end. We'll have about 2 to 3 minutes for you to ask questions. So be ready for that before we transition to the next speaker. Okay? And for folks who are joining us virtually, feel free to go ahead and send your questions. Captain Caboose will ask them. With that, I think we are then ready for the first presentation on geomagnetic source. Sir.
The click. So there's a clicker.
Yeah.
Survivability class, welcome. My name is Annealing, and I'm a senior for university at West Point and space science major. And my name is Ahmed Al-Ghalaibi. I'm from company G2, and I'm an aerospace engineering major. I'm a sophomore or a yearling or what's confidence here. Yeah, I'm a research advisor to Dr. Derek and their criminal labs. And so our presentation, so our research is on characteristic of pulsation during geomagnetic storm and April 23, 24, and 2023. And basically, it's a space weather research. And space weather is similar to the weather that we know in Earth. On Earth, we have a hurricane, we have typhoon. In space, we have weather as well, but the main driver is from the sun. So solar activity such as solar wind and solar eruptions that will impact on their environments that cause space weather. That have a lot of impact on satellites, the power grid, all kind of different stuff in Earth. And then just thinking about Earth is like a big bubble that this bubble consistently off the magnetic field, and the solar eruption when it hits the Earth, it oscillates and shaking the bubbles, and we can see that signatures on the ground. Next slide, this is our overview agenda, and it's so basically the overview. What we're doing here is magnetic pulsation. It's basically the oscillation or the shaking of that Earth bubble, and we can use the ground magnetometer on the ground to see that signatures. And some of the key findings that we'll dig into later. Yeah. So first of all, introduction. What is magnetic pulsation? Like I said earlier, it's the oscillation for the shaking of that Earth field lines in ultra low frequency range, and we can see that from the ground. And it's very active and complex during geomagnetic storm. So that's why we're trying to relate the pulsation, what happened in the space. Next slide. So of course, in our profession in the Army, we really care about the so what. So here's the military relevance of the effects that this might have. So here, as you can see, the highlighted in yellow are some of the indirect effects that it might have on the like storms on like military applications. We can see a lot of these, the effect is degraded range and accuracy for a lot of our systems. So of course we have to keep that in mind when we fly, and so we have to do it accordingly. So we know if there's a certain storm, we have to keep this in mind. And here for the red, this is probably the most important thing, is it has a direct effect. For like electrical transformers, it causes grid damage, power outage due to the geomagnetic induced currents. So we can actually see a case study in Canada where a storm actually occurred, and the geomagnetic magnetic induced currents actually caused a power outage for 6 million people for 9 hours. So this shows the scale. This might have on like and it's like a nationwide scale. You can see like how many people were affected, and for the duration, since 9 hours, it's not a short period of time. So yes, some of the factors business, but then the pulsation basically tell us what happened in this space and what caused those magnetic pulsation. We have a different frequency classification for pulsation from PC1 to PC5, and PI1, PI2. Those are based on the frequency range. So there are several common causes for each of the classification. For example, PC3 might caused by the first interaction between the solar eruption to the Earth, and then usually we see that in the PC3 frequency range. Whereas PC1 is a little different. There's wave interaction in the radiation belt. So we try to understand what frequency distribution is within that geomagnetic activities, and how does the strength of pulsation evolve during the 23-24 April storm. Yeah, so moving on to the data and methods. So basically, we're looking at first of all, we use wind satellites to tell us how is this solar eruption looks like. So the orientation, the speed, and all that. Supermag that tells us magnetic field perturbation on the ground. So it's based on that measure, we can link to what happened in the space. Ampere is just an indication for substorm events. So a substorm is basically one of the geomagnetic activity that happens in high latitude and night side, and usually cause the northern lights. So if you heard about substorm, you can think about northern light. This is connected. Next one. So this is the ground magnetometer station in Alaska on the left, and the Canada right. So those 20-ish stations are the data that we pull out from. And next slide. So we get the raw magnetic field data on the left-hand side. This is directly pulled from Canada and Alaska. Then we calculated the magnetic field perturbation, and then we use bandpass filter based on the frequency that we talked about earlier, the classification of pulsation. Then we produce a spectrogram. Basically, it tells us the 2 days event from 23 to 24, the x-axis, and the y-axis tell us what's the frequency range and what's the strength of the pulsation. So yellow means strong pulsation, whereas the dark blue tells us there's a quiet events, nothing happened. And then we produce frequency spectrum. So we basically pull up. We're interested in what happened in this strong pulsation. We pull it out and see frequency ranges versus the relative power, and we try to see where the PC3 or other range has a strong response to it. Next slide. So this is our timeline. What happened? It's 23 to 24 April. There's four important events that are happening. The first one is the foreshock, and the second one is the substorm, super substorm, then the substorm, and the last one is the solar wind orientation and some of the bioshock changes. Okay. So the first event is the CME foreshock. It's basically the first wave that the solar eruption hitting the Earth, doing that bubbles, and we can see there's some little response on the pulsation. And if we pull out the frequency spectrum, we saw a PC3 has the most strongest response to it. And next slide. So this is a super substorm, second event. It happened at 04 UT, April 24. Only lasts about 5 minutes. It's not very common, but it's really strong pulsation. As you can see in one of the magnetometer station, it has a really strong pulsation response. And just ordering to you guys, what are those plots? The first two are the solar wind orientation. So like the solar wind has different orientation hitting the Earth. This one is the alpha speed. It's basically how the wave traveled along the magnetic field line. And then the particle number density. Next is the basically tell you the strength of the geometry in the storm. This one is basically you use this as a substorm indicator. And then from here, you can see more clearly what happened here. 12 planets facing the sun, and this is a night side sector. And we played the video. Yeah. So you can see how that substorm event. This only lasted 5 minutes, and that's basically with this LT index, the local time index with special graph, we are able to identify some of the substrate posture. And next, we move on to from the minute pulsation, basically tell us PC4, PC5 have a strong response to it, but it's really hard to just looking at the spectra and tell there's a substrate. So we need local time index plus the spectral rate. So what it does tell us is that the substorm can lead to a strong minute pulsation, right, during the in mid latitude to high latitude stations. And for commander, that means the communication disruption and reduced GPS accuracy, and so as a radar system error. So this is just another case of a substorm, and yeah. Next. So this is the what we call a broadband signature, whereas all the frequency range has the same power. And really, it's very hard to just use this frequency spectra to identify the substorm offset. Next one is a solar wind condition. Basically, solar wind orientation has an impact on pulsation in stationary polar regions. So, commander is just the one takeaway is that the solar wind can have impact in polar regions, and we need to be careful of that. Thanks. So this is the sub-Alpine conditions. This is whereas the Bauscha can kind of disappear, and then you also have a strong positive.
Yeah, about 30 seconds to a minute left.
Yeah. So this is the end of the storm, and then this. So one takeaway from it, the assets in the high latitude regions are vulnerable to solar wind conditions during geomagnetic storm, and then the local electric systems on the power grid in the mid latitude, high latitude regions can be disrupted by the substorms. And that's a reference, and that's our group. And more any questions? Sorry. All right.
Can you go back to your slide 15? Something to make the other maybe go forward line to that figure that can you explain that again?
Yes, I think it's that. Yeah. So basically, this is tell you the red plot. It tells you the strength of westward electric jets. So basically westward current system, and we usually use that for substorm onset detection because the substorm is coming from the night side of the Earth and hitting the Earth. So we're trying to see. We're trying to see if we can use this to indicate a substorm. So basically, it's a substorm indicator essentially.
What is the axis going around of the surgeon?
So this axis is just the strength in nano testing. And then so if we're thinking about the substorm current, sorry, there's something called substorm current wedge, is where your night side substorm connected to Earth ionosphere, and then it will move westward. And this is the westward electric jet current system. So basically, you're looking at the strength, and then this is what tells you where it comes from. So from this is at night side, and so there's like other plots that show you like the night side, the red was like split to 1,000, 2,000, yeah, the night side, and that's how you know all that should probably have such a right.
Good morning, everyone. I'm Ken Short. I'm today like to look at Ken John Sykes. We'll talk to you a bit about our research this semester and our work on low Earth orbit neutron incidence detection for annealing systems, or as we like to call it, LEONIDAS. We did a brief. We're going to talk about our problem statement and specifically the issues we plan on addressing with our work. Then we're going to walk you through our solution glide path and the steps we're taking to actually address the issue. We're going to describe simulation as a scientific process and then walk through the simulators we work with this semester. Then we're going to walk you through our data collection process and talk a bit about results conclusions we've drawn. Starting with our problem statement. Space assets are foundational to everyday Army operations. We use them for geopositioning, navigation, for SATCOM communications, pretty much anything that we do in terms of targeting, reconnaissance, like you could name any sort of Army process, and there's a functional space asset that we use, that we leverage in order to make that happen. But these capabilities are vulnerable to EM-based enemy attacks, as well as ambient radiation in the atmosphere, specifically space weather events like we just talked about. And we want to go about addressing this and making these assets more reliable and increasing their longevity to get more bang for our buck in terms of utilizing them. So how we plan on doing this, our solution glide path, we think that simulators present a unique opportunity for a diagnostic sensor system that can be used to inform operators on what EM effects are impacting the function of space assets. Specifically, we think that they can be used on board in a satellite bus unit in order to characterize and get a formal understanding of what radiation is incident with electronics that are in space. That way we can address those issues with either non-active defense measures such as shielding or more counteractive measures such as thermal annealing. So as far as our timeline goes, walk through here at the bottom. Right now we're in the screening candidate simulator stage. We've identified some of the traits that we think would make candidates viable for use in space or use as detectors for diagnostics. We've found materials that exhibit them, and we'll walk you through that in a later slide. And we've conducted a single field analysis to get a baseline with the materials and understand a bit about what their output pulse shape discriminations look like. After that, we're going to work on characterizing outputs, specifically in mixed field analysis. We're going to introduce more sources that are more pertinent to the space domain and use pulse shape discrimination to identify and distinguish between different sources as we go through. Then we're going to work on designing a payload, identifying design limitations, and working to use commercial off-the-shelf products in order to build something modular that can potentially be used in different satellite buses. And we'll conduct lab trials with that specific device and iterate on the design process as we see needed, and eventually coordinate a launch in order to acquire data in the local lab.
All right, so for anyone who might not already know, a scintillator is any material that's able to do a process called scintillation. Now, what is scintillation? Scintillation is when a material absorbs a high energy particle, such as a gamma ray, an X-ray, a neutron, any kind of radiation source, and is able to emit a photon. Using that photon, we're able to multiply that to get a stronger signal and record that photon as one count, and from there, check our count per second and propagation. So when choosing what kind of candidates we wanted, or what kind of scintillators we wanted to test out for this project, we wanted to choose candidates that, first of all, had good radiation hardness. This means that it's resistant to any damage that might be caused by the high energy particles, specifically in space. We wanted materials that had high atomic numbers, because high atomic numbers in scintillation, it promotes a lot of inelastic scattering, which is great for slowing down fast neutrons as well as absorbing more radiation to get a better efficiency. We also wanted a large density, because when you have a larger density inside of your scintillation material, that means there's more molecules per unit volume, meaning there's a higher chance of interaction and therefore higher efficiency. The three scintillators we chose, the first one was VGO. We chose this one because it had a really good energy resolution, meaning that when it's able to detect radiation from a bunch of different energy levels, say like low energy radiation gammas to high energy radiation gammas. We also chose zinc tungstate. It's not quite as good as the germate for energy resolution, but relative to the industry standard, it's still pretty good. And finally, we chose cadmium tungstate. And for cadmium tungstate, while it may not be the best gamma detector, as we showed with VGO, it does have a high thermal absorption cross-section, which basically means it's really good at absorbing thermal neutrons, which is what we want, because that's how we get counts and how we're able to determine good efficiency of real detections. So going to our data collection, right here is just a block diagram of kind of what our setup looked like. So first we have our button source, which for us was just a simple cesium-137 source. From there, we mix that alongside our scintillator material, which I saw in the previous slide. that was set up next to our PMT, which stands for photon multiplier tube. That just absorbs the photons that counts. From there, that PMT goes to an oscilloscope. We're able to analyze the pulse. We're able to analyze the pulse and get a reading on every count. That's sent to a digitizer that converts that digital signal into an analog signal that our computer can read. From there, we set that all up in our computer.
Other results. So we tested the 3 simulators that John mentioned earlier with the cesium-137 source. The first of which was physical Geomagnetic. Before we took readings from the source, we first did it on counts. This is measuring basically atmospheric radiation that's getting into our center. We had a light type box. Despite that, we're still getting another 20 counts of photons per second. When we inserted our cesium-137 source into the setup, you can see that we have a much higher incidence of photons. This is around 1400 counts per second. And you can also see on this PSD graph, the data is very visible. We have a super high amount of counts around ABC channel 100, and we have a very large visible tail that you can see where our data is. The next source we tested was cadmium tungstate. We see a very similar dark graph to physical Geomagnetic, which makes a lot of sense, but again, just measuring basically the atmospheric light at this point. Our data for cadmium tungstate is a lot more compressed in terms of ABC channel, which basically represents the maximum voltage of each pulse. On our PSD axis, we see that the data is a lot more spread out. So this is much less distinguished from the peak, much less wide candidate on detecting sources specifically. And then on the zinc tungstate, again, very similar graph. Zinc tungstate has very similar signature to cadmium tungstate in terms of being exposed to a gamma source. For this, it's even more compressed on the ADC channel axis and about as spread out as the cadmium tungstate was on the PSD axis. So again, not as valuable as detecting specifically gamma radiation as B2.
It's pertinent to note that a lot of our findings are pretty consistent with existing knowledge state of the art. So that's kind of what the point of work this semester was. We kind of established a baseline and get to that point where we can utilize it effectively and get system readings.
And on our conclusion, so next we'll require simulators with different PSD signatures for both fast neutrons and gamma radiation sources. So despite zinc tungstate, cadmium tungstate not being as viable sources for detecting gamma radiation, they might have PSD signatures that are very distinct from VGO when it comes to detecting fast neutrons. So using both measure detector with either cadmium tungstate and zinc tungstate with VGO would be a really viable option. So we have to continue testing each of the sources in gamma field.
Additionally, we've read some literature that talks about the potential application of thermalizers that are layered in with the cylinder material itself. So the idea would be that something like PMMA, like a plastic, would create a better opportunity for inelastic scattering to occur and slow down incident radiation and allow for more interactive as well as other than that, just remain class with our presentation. Any questions?
Yes, go ahead.
Yeah, Scott Ransom from the University of Virginia. Very nice presentation. So my question is really about you're trying to optimize the simulators for fast neutrons. What is the primary source you're expecting to detect fast neutron wise? Is this non-proliferation type work? Is it some kind of astrophysical source? Is it from the sun?
So we want something that's kind of got more of a broad spanning use. So we want to, that's kind of our next step is identify pertinent sources that we want to start optimizing for. Specifically, we want to focus on like incident cosmic radiation stuff that is just kind of exists ambiently in low Earth orbit. But we also like the idea of artificially, I think Operation Starfish was where there's like a nuclear detonation in space, and we're interested in exploring what those type of effects have on space assets and frankly any asset that's on it as well. So that would be something that would be interesting in trying to.
Great question.
So yes, it's all the above. Any other questions?
If you go back to your slide that had the results, this one's fine. So on the lower left, why is the data kind of? Why does it? See what it's like, an arc, that'd be like a lot of the.
So this has to do with how our data is discretized, it's been converted, it's digital. Station to a tag log source, and the computer can read it. It's just how I understand it is when the data was transferred over, if you say had a value of 6.72, it was either placed inside within of 6.7 or 6.8. It was almost kind of rounded. So that's why you see on the 60 line shape. So it looks like the points are almost lining up. That's why it has an image.
And there's one quick question for you all. At the beginning, you talked about, being able to help with electromagnetic attack and radiation is just sort of inherent in the environments. Do you hope that you'd be able to use this to sort of distinguish between these sort of, does it not know which is which?
Yeah, that's absolutely the goal. The reason that we think that Scintillator offer a unique opportunity for this is because specifically it uses pulse shape discrimination. Once we take readings of different potential attack sources or ambient sources, and we get readings that allow us to kind of characterize what those signatures look like, we can use our reference pulses to kind of distinguish what we might see on the actual source itself.
Isn't it the benefit then of using different multi-sensor or a multi-factor sensor because they have different strengths as far as what they can.
Yes, sir.
You're the experts in the room. We're just trying to present it
No,
out.
that's true. That's true.
All right, let's thank them again. Take you on the material cloaking. I would like to take a moment, particularly because many of you have just re-entered the room, to just kind of remind everyone of how the rest of the session will go. Okay. One, I asked you to be respectful, right, of the speaker, make sure that any additional lights you have are silenced. I would ask that you be mindful of the fact that we have a camera on the back. There's some who couldn't be here with us today, who are joining us virtually, okay? And so just be aware that we are broadcasting this live. For the speakers, what that means is if you turn and face your slides, the microphone will not pick you up as much as if you actually talk to the audience. Okay, so just be aware of that. And then if there's anyone who's joined us halfway through the session, just know if you have questions at the end, put them in the chat and Captain Caboose will facilitate your questions and make sure that they are asked. Okay, so you have the ability to do that. For the rest of you, right, at the end of their 10-minute presentation, at that point then, I will open it up for a couple of questions before we transition to the next speaker. Okay, you have a small clicker there that you can use to flip through the slides. And then you found the pointers, so you should be good to go. If you are ready, you can start whenever.
Welcome all. Introduce to you the material cloaking through synthetic replication of the Macrosteles, Fascifrons, Brochosome geometry. My name is Cadet Elaine Joyce, and I'm presenting on behalf of the Mechanical and Aerospace Engineering Department.
I'm Cadet Benjamin Garcia, representing the paint department.
My name is Cadet Shanara Smith. I'm representing the electrical engineering and computer science department.
I'm Cadet Pierce Baswitz. I'm representing the Mechanical and Aerospace Engineering.
Introduce to you the modern warfighter's problem. It is no longer safe to assume that operations conducted at night are concealed from our adversaries. Additionally, as further technology across the globe improves, it becomes harder and harder to conceal our assets on all levels of the multi-domain operational environment. This introduces our problem statement. Develop a method to conceal U.S. military signatures. We have found a possible natural solution.
So spiders and birds both predate on the ultraviolet light spectrum beyond human vision. And despite this, the leaf hopper still remains difficult to detect. It has a passive optical concealment, which effectively suppresses reflected light by up to 94%. But, and importantly, this is both consistent and independent of many factors such as the weather, terrain, the temperature, and the orientation. And what gives it this property is not the organism itself, but something much smaller. The leafhopper produces a microscopic particle called the brochosome. The brochosome is a hollow, nano-sized structure with highly ordered surface architecture that gives it the scattering and suppression effect. As depicted on the left, under visible light, the leafhopper appears normal, but under ultraviolet light, as depicted on the image on the right, the leafhopper appears to have a dramatically reduced visual signature. Now, this naturally occurring cloaking mechanism is a blueprint for what we can do to engineer materials to reproduce the same control on the electromagnetic expressions of objects.
Now we're going to talk about our research approach. And so we began this process by understanding our biological field. It was very difficult as a whole to understand what we need to do and how we're going to do it. And so by understanding the leafhopper and this particle geometry, we were able to then format what we wanted to do moving forward for this progress. The next thing we did was we implemented the design into SolidWorks CAD software. And so we just designed this particle that you see on the counter there in this software, and we both use that as a blueprint for CST simulation and digital testing, as well as 3D printing it so that we can physically test it and physically validate our results in the future.
The theory that governs our work is simple, right? On a conventional surface, incident light reflects directly back toward the observer, which allows the object to be seen. The reflection is governed by Fresnel's equation, which determines how much light is reflected based on the angle of incidence and the material properties. Our goal is to control the interaction on the surface level so that the reflected light is no longer returned directly to the viewer, but instead is suppressed or redirected. In this case, the brochosome surface changes how light interacts with the material. Rather than producing a strong specular reflection, the energy is scattered and redistributed, reducing the return signal. That is the fundamental principle behind the cloaking effect that we are studying.
At the core of this design are two governing principles. The first is my scattering. This effect occurs when the wavelength of incident light is on scale with the diameter of the particle that it is interacting with. What this basically does is it directs the light away from the direction of incident. In addition to my scattering, the through holes within the brochosome also play a part in why it's such an effective anti-reflector. When incident light travels through the through holes, it gets coupled and trapped within the hollow sphere inside of the particle. This basically, instead of reflecting the light back, it gets absorbed and scattered in the same direction. And together with my scattering, this is what makes the brochosome such an effective anti-reflector.
Ladies and gentlemen, I introduce to you the Archimedes icosahedron, better known as the soccer ball shape. Notice the negative cavity, right, which accounts for two phenomena, the my scattering effect and the through hole effect. Notice the symmetry, which eases the mass production of this molecule. This molecule specifically is made of ABS plastic, which further increases the manufacturability of this product. The brochosome, as seen here, is 3 centimeters in diameter, which correlates to between 3 gigahertz and 10 gigahertz wave.
So we started our simulations with individual brochosomes. On the top left here, we see the incident wavelength is around 10 times the size of the brochosome. As we move to the right, on the top figure, we can see how as the wavelength of incident light approaches the diameter of the particle, it becomes a lot more forward focused. In addition, as seen on the bottom figure, as we move from an incident wavelength of the size of the diameter to the size of the through holes, which is about 1/3 of the particle diameter, it gets even more focused away from the direction of incidence. These two effects and these simulations helped prove that these effects and kind of helped validate our theory on why these brochosomes act the way they do. In addition, we then decided to simulate these lattice structures. The top figure here shows a straight lattice where every brochosome is surrounded by 4 other brochosomes. And the other lattice that we simulated was a brochosome surrounded by 6 other brochosomes. And the results from these 2 simulations were practically the same. This kind of helps prove that it's not just the individual, it's not just the structure of these brochosomes that create this effect, but it's also and mostly just the individual structure of the brochosome that creates the anti-reflecting properties.
The next step of our research progression is physically validating these results that we found in the CFT software simulations. And what that entails, following our experimental design, is transmitting an RF signal to an antenna and recording the full spectral trace, as well as, most importantly, the absolute maximum of that trace. And in doing that, we aggregate that maximum with the other through a frequency sweep to create a frequency response curve across that sweep. And with that, we can then focus on the dips and powers that actually show the attenuation occurring due to the brochosome's design. And along with that, we will then be able to confirm what we hypothesized in the experiments in the software simulations.
Looking forward, the next step will be to prove experimental validation of radio frequency signature control. Again, just as Gennaro said, we're going to be physically testing these brochosomes to ensure that the effect still remains within a real world environment, not just on simulation. Additionally, after that, our far goal is to shrink the brochosome down to the scale where it is effective at optical frequencies. So there's a potential in having it protect signatures on the scale of UV, infrared, and visible light. And our image here represents that vision. A platform that is significantly reduced in signature, and it is specifically at the UV spectrum. And we can foresee this concept being used in modern military applications and in modern warfare.
Ladies and gentlemen, this is our future. This is how we regain our advantage on the battlefield. Thank you.
Well done. At least one of you should have a career in sales. I can certainly see with that one and that one, how you can affect things at gigahertz frequencies. And you said your goal is to get to like IR-ish. My question is, how would you manufacture something with the geometrical fidelity of that at like a 145 micron diameter?
That's a great question, sir. From the mech side, we're the 2 mech majors in the room. We kind of thought like a lot about like the future reproducibility of this product. And so on that scale, the printers that we've been using currently in the mechanical and aerospace engineering department can print accurately about to the size of my pinky here. But beyond that point, you start to see the ridging on the print starts to overcome the size of the actual structure. So that's where you run into issues with that. And so unfortunately, the only way we can address this problem is to find printers that can print that accurately at that level. And so there are 1 or 2 printers that have currently done prints accurately to that scale in the country. And so that's sort of the next step is to, once we see physical validation, start reaching out to these see if they will help us out.
Yeah, nice job on the presentation. So because the wavelength of the cloaking ability is based on the size of the holes, so that means it has a relatively narrow wavelength range. So if you wanted to protect something, say, from IR through UV, let's say, do you anticipate having to have a range of these things of different sizes, or how would that work?
So, we're still at the beginning part of our research with this.
Yeah, that was the first one.
But after we begin seeing physical simulations or physical experiments, we can then start to incorporate different size chromosomes and maybe a mix of different sizes within a singular lattice. And potentially that could have the same effects. There's still a lot of testing, and there's nothing that we can like positively say for sure, but it is something that we will be looking into in the future.
Another possibility is to have a multi-layered like material. And so it would have different size brochosomes cascading sort of in the materials. We have no idea how this would act, but that's another route we can take.
The advantage of this being, the effect being found in geometry is that the scalability really of, just using simple materials to create a wide variety of sizes does make that idea possible.
We have one question from online. It says they may have missed this, but any idea how movement, weather changes, or damage would affect this concept of cloaking?
So I will add to that because I'm a tanker. And when I drive my tank around, I drive it through everything. I will drive it through trees, like knocking the tree over. So I'd be curious about, what material considerations you thought about, and as opposed to plastic, deal with that.
So what's really interesting is the material property of the brochosome doesn't have as much an effect as you might think it does, as opposed to what the physical geometry of the brochosome does to the incident. There's plenty of other research that have gone into the different materials that you can make this out of. And from what we've seen so far is that there are other researchers that produced it out of nickel, titanium, aluminum, and the effects were practically the same as well. So we also perceive a use of a multitude of different materials depending on like the situation that they will be used.
And the brochosome as a whole does not require power. It is waterproof. It can get muddy and dirty, and it will still have the same effect.
Interesting.
So long as the mud doesn't plug the hole.
Yeah.
You can, spray it off, I'd say, and then.
Yeah, I mean, it would also have to do with the size of the particulates within the dirt, and if that has additional interactions with the incident. So like at a really big scale, probably not, but at a small scale where the particulates are the same size as the brochosome, then perhaps choose.
All right, thank you once again.
Yeah, we gotta move on.
Okay, and our last presentation will be on variable length hoist.
Morning, everyone. I'm Cadet Stanislav, and I'll be presenting the nonlinear dynamics of variable length hoist for Medevac operations. My advisor is Lieutenant Cat, and in context, I'm a mechanical and engineering major. Like those in the streams, also share a passion for physics and how it can use physics to help the greater world. Additionally, if you're visiting, I want to say thank you for coming. I know there's a lot of other projects going on right now, and I want to express my gratitude for coming to watch my presentation. So one of the dynamics, we're going to begin with a problem statement, the current state of the art. So, problem statement, the current state of the art, and my MATLAB solution, going through a tracking demonstration as well, and broadening as well. So what I plan to do afterwards, along with the conclusion. So what is the problem statement? The U.S. Army's Black Hawk, also known, the U.S. Army's Black Hawk medical evacuation system, also known as the jungle penetrator, is subject to extreme swing angles, which has led to loss of life. So the effort right now is to be able to dampen the system using micro lengthening and shortening. So this based on the underlying principle of physics, more likely the governing equation of pendulum physics, where if you have something swinging down and it's shortened as theta equals 0, the swing angle will increase to the increase of kinetic energy. Whereas if it's lengthened as theta equals 0, the system will be effectively dampened, decreasing kinetic energy. So the current state of the art. So far, this project has been current state of the art. This problem has been explored by Lieutenant Colonel Capps and Virginia Tech's Dr. Lanzaretti, who conducted planar pendulum tests through a video to gauge whether damping is an effective solution or not based on the micro lengthening and shortening. And right here is an example of the swing demonstration. And if you guys are familiar, this is the aerosol powered where there are plenty of good members right there. This right here is an example of using the manual pulley system to try to dampen the payload. If you look closely, you'll see the payload being extended as theta equals 0 and then pulled up when the theta is at its max. Also take note of the payload disappearing off the screen off the left, and additionally the amount of kind of objects within this vicinity. So receiving those videos in the past semester, I came to these 3 conclusions and limitations. One being of the lack of extreme angles, of course, on a jungle penetrator. The people on the casualties on the jungle penetrator could be subject to more extreme angles greater than 30 degrees. Another one is also the lack of simulated larger mass. So the jungle penetrator is rated up to 300 pounds, and that payload is probably around 3 to 5 kilograms max. And lastly, this was tested in 2D planar swings, whereas, of course, on a jungle penetrator, it could be in a 3-dimensional case. However, based on this governing equation, that shouldn't really matter as much as it's only dependent on the lengthening rate of change of the length, which this as a whole determines the adding or subtracting kinetic energy to the system. Additionally, from receiving those videos, I found the large constraint being the swing angles disappear from the frame, which are correlate to a lack of data for when the payload is on the screen. So one solution, which was explored by Lieutenant Colonel Capps, was going through a tracker software, which clicks through where the payload was for each frame and do some short calculations. If there are around 10 videos, each are around 3 minutes long, and the video is being recorded at 60 frames per second, that would be at around 110,000 clicks. So I want to say thank you, Lieutenant Colonel Capps, for going through here these videos. However, it does result in this very clean data. So to orient you guys, from 0 seconds to around 130 seconds, this is where the payload is being dropped down, and this is where the payload is starting to get set up by the cadet to be released. So ultimately, at around 130 seconds is where the swing actually starts. And to orient you guys to the graphs further, this is the energy density graph. This is a length over time graph. And then this is the XY graph. So this is the overall tracking of the payload. So if we start at 130 seconds, you'll see the micro lengthening and shortening of the payload. And if you correlate that down to around 130 seconds here, you see a dramatic decrease in the energy density, thus confirming that damping is valid and that micro lengthening and shortening of the payload is an effective solution. And of course, this goes back to the governing equation where kinetic energy is either lost or gained based on the change of length. However, as a mech major, I wanted to find a faster solution and do this automatically through MATLAB using the computer vision and imaging processing toolboxes in MATLAB. The computer vision toolbox is able to process videos, whereas the image processing is able to distinguish items within those videos. So the method of the MATLAB program simplified is that it gains the video background, then I cross out an ignore zone of the cadet to make sure nothing is identified within that area. Then I also identify the origin point for the length, coupling that with the initial condition of the cable length, which is then able to create units for the graphs. And then as the program runs, the video then gauges what is a likely box. And then this is where the asterisks are, is where the biggest bugs and roadblocks of the project were. So when the object disappears, the MATLAB code then enters the loss mode, which then gauges where it left on the frame and then where it will soon re-enter the frame. And based on deciding where it re-enters, it then re-picks up the object. Whereas beforehand, when it disappeared, it would just falsely identify another object, creating more noise. Then after that, the MATLAB program computes coordinate and velocity graphs. And here's a demonstration of the tracking software. As you can see, it starts leaving the frame. And take note of the noise over here. So there's a false identification over the dead head as it releases it. And this will later show in some noise graphs. Then if you skip ahead, so you're on 1 minute. This is where the major roadblocks of the project resolved was being able to re-identify the box as it goes into the frame. So what does this mean in comparison to the other tracking software? If you look closely, there are very similar data plots, both spanning around 8 meters in range. And looking closely, there are around 4 swings before it's dampened. Of course, as I noted within the initial swing video, there is some noise near the top, but where the program falsely identified the box, and just show of where it identified over the dead set in the previous demonstration. And then looking at where the initial swing is versus my data, there's very similar points where there are around 7 minimums and maximums of micro lengthening and shortening. However, my noise contributes to some lack of data there. To try to solve this, I could either solve the actual processing itself within MATLAB to have better weights to identify what's the box and what is not the payload, or I could also go through the actual graphs themselves and smoothing them out there as well. This course, in conjunction with my computational analysis class that I'm taking, where I'm learning a lot of these techniques to apply in this project. And what I plan on doing from here. So learning Simulink in class, I want to try to simulate this through running through different amounts of data. So through Simulink, I could be able to edit the different rates of change of length. As I was. I could change the different rates of change of the length, additionally this initial start angle, and the length of the cable. And this right here is a spring damper system. However, I can quickly do this within Simulink. And additionally, I plan to do this automatically. This was the manual pull-up system, but I plan on doing this with a Arduino motor and a motion sensor. And through programming, I want to be able to do the pull-ups automatically, thus increasing efficiency and being able to test different constraints such as higher heights and longer lengths and greater angles as well. So to conclude, my current plan of action is to apply the software to each of the 10 videos. To complete the paper, verify the utility and damping effects of variable cable pull-up, which was confirmed with the tracking software, along with modeling the various pull-up speed and angles through Simulink. As for future considerations, I want to create an automatic system to do this based off a motion sensor and physically test this, hopefully on a drone, with longer cable lengths and larger angles. Sir, ma'am, cadets, I'm Cadet Senizol, and this is my presentation.
Yeah, but these are no more questions.
Thanks for a very good presentation. So on slide 8 or 9, when the clicking is happening? Yes, so in that diagram on the right, what's the middle line?
This middle line over the 3-minute video. This middle line is the box being lowered and then being set and pulled back by the cadet and where it'll be released. Sure.
Yeah, you mentioned that this is micro lengthening and stuff. What is the fractional change in length? And is the amount of damping proportional to that change? Like if you have a longer length change, Is it proportionally more effective?
It's proportional to the length of change, but also the speed of how it's being changed. Based on this equation, so of course, it'll be proportional to like the amount being changed. However, if you're able to increase the speed of where it's being changed, that could also help decrease the energy as well. And of course, could be resolved and seen through doing a simulant demonstration where I can change like the different rates of change of it and also how long it's going.
Can you see that length change in your data of the, like, where is the length change in there?
The length change is over here, so this is being dropped, and then as you see, it's going back up again, which will be either increasing or decreasing. But over here, this is probably around consistent amounts of length change, so that'll be another thing that I can explore as well. Thanks.
Thanks.
So in this experiment, was somebody like manually changing the length?
Yes, sir.
And so were they just kind of like looking at the?
You're looking down, and then
Okay, so, let's say they did a bad job. Could they actually make the oscillations increase in amplitude?
yes, sir, they can. So based on the governing equation, if they policy like think if they pull the cable up as it's swinging down, that could increase the energy. So that's why I'm trying to go in the effort of automatically doing it based on the question. So whether the velocity decides maximum or minimum to dampen it at the best time.
Session lens. You go to go to your first data files. Yeah. So so like if the box goes off the frame and you miss your data is effectively incomplete there at the bottom of the do you make sense to try to capture the motion of the string maybe and then make some assumptions about where the box ought to be linked?
So the problem with that was since it's variable length, like those assumptions can like be nullified because it's not a constant pull. If it's a constant pull up, then you can code that in. But since it's manual and somebody's controlling it, those like assumptions will be a lot more false because at the end they could either be not pulling it up, or lengthening it. Since it's like user control. So that's something I try to explore through, but I noticed that like the best approach of that was just to leave it blank and then to try to analyze it from there. If the videos were redone, definitely use watch people step back furthermore, but
Yeah, I maybe we talk afterwards. I have some thoughts on like potentially how to recover a decent estimate.
Thanks. I could definitely go and like re-entry and then.
Okay, once again, thank you. Being here as part of the session. So to have you all, and I think there'll be another brief break before we get started with session 2.
So my name's Ian. I'm a pitcher on the baseball team, and I wanted to use my love for baseball to kind of dive into some physics and see how I can make myself and my teammates better. A little agenda. We go through an introduction to natural inspiration, the objective of my research, data, results, operational applications, and again, the work cited. So my interest stems from things that fly, like fighter jets, eagles, golf balls, and again, torpedoes, which rotate in the air, or in the water. This all leads me to baseball. So a couple of things I used at the beginning of my research was the coefficient of drag and lift coefficient to look into things like the Magnus effect, which characterizes the different effects on a baseball as it rotates through the air. As it's rotating with backspin, it's moving through the air, and the air is moving. When the air is moving with the spin, it creates a lower pressure, and when the air is moving against the spin, it creates a higher pressure, effectively creating lift on some pitches, like a forcing fastball from a tall right hand. Or your favorite Garrett Cole, or anything like that.
So that's what we're trying to do more of. Looking into the natural inspiration of baseball, when the ball is released from a pitcher's hand, the sphere interacts with the airflow through phenomena such as magnus effect, seam-induced turbulence, and boundary layer separation, which contribute to all the different metrics, the nonlinear metrics of a baseball in flight. So again, the objective is to characterize these nonlinear dynamics of the baseball with the purpose of validating the aerodynamic theory involved projectile motion by multi-pivot pendulum dynamics, which is shown here at different, as every pitcher has a different release height and ways of getting there, which all adds to the metrics of the pitch. So here's the pitching profile for me as a pitcher. My fastball is about 85 or 88 miles an hour. My slider could be around 80 miles an hour, more typically being 77 miles an hour. My changeup being a lot like my fastball. It sits around 83 to 84 miles an hour. So as you can see with all pitches, I have a consistent release height. However, the extension differs from every pitch, and that is how far my arm is actually getting out to get these pitches where I want them to do. And the max horizontal movements differ rather heavily from average. So as you can see here, my max horizontal movement on my fastball is 23 inches of break, where the average is around 18. So this gives me an insight that there is a optimal window that I can hit to make my pitch as good as I can be. And the same thing goes for my changeup and my slider. So here are three pitches I looked at in depth. And as you can see with the metrics, they have relatively same velocities with the same spin rates, the same release height and extension, and spin efficiency, which calculates how much the spin is actually contributing to the movement of the pitch. So at 94% spin efficiency, about 94% of the spin rate of this ball is actually contributing to the movement. And as you can see, although the metrics of these pitches are quite similar, the actual, what I like to define it as the turning point is completely different. Since I'm a sidearm pitcher, I get a lot of my effectiveness in how much my ball actually moves. And with one of my pitches being 21 inches of horizontal movement, and another being 15, with rather identical metrics, this sparked a curiosity in seeing how could I efficiently, make my pitch more consistently in that 20 to 21 inch range. So as you can see here, though, with all these metrics, the main difference is the axis tilt. One being 3 o'clock, one being about 2:30, and one being 2 o'clock. So this kind of tells you where my hand is when it, or where my hand is on the ball as the ball comes out of my hand. So at about 3 o'clock, I'm getting full side spin, and the magnus effect we talked about earlier is acting laterally with my pitch. Rather than giving it ride, it gives it some depth and arm side problem. So here are the results. Right here is a histogram of the pitches and the axis tilts that we just spoke about. And the blue is going to be about my fastball, the green is going to be my slider, and the purple is going to be my changeup. So for my fastball, we can see a tight cluster right here, and that shows the consistency in the frame, the range where my hand is when I release the pitch. And the same thing goes for the changeup, even though there's less frequency in how often I throw it, shown by the histogram. And the slider shows inconsistency and variability, and ultimately more complex spin behavior, as there's a wide spread from about 8 o'clock to 11 o'clock. So just for a visualization, instead of releasing side spin at 3 o'clock with my fastball, my slider is going to be here as I get around it to induce that movement. So
each pitch type, they occupy like a distinct window of optimization. Or, I guess they each have a window of where I can throw it to best optimize the movement. So for my fastball, we'll see here in the next slide, it's going to be around right here where the tight cluster is. Yes, I don't know. I got to put the schedule. So right here is a horizontal break in pitch type polar that scatter chart given the axis tilt. So as you can see, I get a lot of my greatest horizontal break around 3, and it's a lot more consistent of a pitch, and therefore we can draw greater conclusions. Same thing with my changeup, even though it's less frequently thrown, we have less data on it. I can draw the conclusion that because it is similar to my changeup, that I'm going to release it at the same spot. But with the slider, we're going to see a trend on the 9 o'clock axis being a lot less than something we see trending towards the 10 o'clock, meaning my window of optimization is going to be around 10 to 9:30, which is a lot higher than window to throw a pitch. Here is the same exact chart, but instead of the bars outward being horizontal rate, it's going to be spin rate. So again, the slider shows a lot of inconsistency in how I release it and how much it's spinning, which is not a good thing for me. But we can see again that right here we get probably the most efficient and optimal spin rate at 10 o'clock. So data supports the objective by demonstrating that the dynamics from a rotating baseball cannot be described linearly. Instead, there exists that optimal window of combined parameters that the pitcher must achieve to generate efficient high movement pitches for different ball pitches. Yeah.
Hold on, I got you.
Yeah, I think it is. So, operational application of rotating projectiles are governed by complex nonlinear interactions between spin, velocity, and airflow. Small changes can lead to large trajectory deviations, especially at long ranges. By isolating a baseball and understanding the the nonlinear aerodynamics of it, we can hopefully target ballistics at making them more accurate and increasing their overall performance. So improved understanding can lead to more precise trajectory predictions and better accuracy at extended ranges. This enables better adjustment for wind conditions, air density, turbulence, wherever you may be shooting, or whatever you may be shooting. And we can maybe help and inform design spin stabilization methods, surface geometry optimization, and more reliable and effective ballistics by just isolating a baseball and studying the nonlinear dynamics. We're excited for the research, and that will include my presentation and the questions.
You actually measure what the spin rate.
So all of this data was gathered at a place called Maven Pitching Labs in Atlanta. This is me in December. There's a, not really sure what to define as new technologies coming out for sports, and this is through TrackMan, which captures everything about your pitch once it leaves your hand. There's completely different methods for getting for setting how we get there. So a lot of these metrics don't even account for what angle my body is at, how much force I'm putting into the ground, how far I'm getting. It doesn't account for any of that, but TrackMan gathers all this information. And this is the unique part about this is it's all actual pitches in it.
How was the research going to affect your training here?
Yeah, so I used to think that I had to worry a lot about my mechanics, but being a sidearm pitcher, 88 miles an hour is pretty good. So I always thought I had to change when is my arm getting behind my head? When am I, maximizing scap retention? All these kind of different things. Where when it comes to the pitch, I'm effective at 23 inches and at 87 to 88 miles an hour. I now know that what I have to focus most on, is the axis tilt. That is all things I have to do with my hand and consistency. I think it helps me and my fellow teammates. We're better able to understand ourselves as pitchers and apply physics to performance.
Any other questions?
I do that. Also the, like it's a window of opportunity you were talking about for optimization is, since I don't have any context behind this, is that like achievable? I mean, can you control, is it achievable? Can you control what you are doing? Like physically within that window, or is the human just always there like random?
Absolutely, that's a great question. I believe it's absolutely controllable. As I talked about earlier, we did not get into any of how I got to the pitch release. This is all about what is happening to the ball in flight. But if I know that I need to stay around 3 o'clock, being full side spin on my fastball, and I need to be around 10 o'clock for my slider, that I can change my mechanics to create different cues for my body to actually achieve these. That may change, my different mechanics may change things like velocity and spin rate, and that all adds to the non-linear dynamics of the pitch. But I believe it's absolutely achievable, considering here that naturally I'm about what I believe is my optimal range. Whereas if I were to drop below 3 o'clock, my pitch would have a lot less horizontal break, a lot more vertical break, and that is just not going to be good for me either. So it's a little bit different when we're talking about the slider. This could go into a lot of different things, such as how I'm holding the baseball, which adds to scheme orientation, and ultimately how the ball is affecting or interacting with the fluid as it goes to manufacture. Yeah, so there's a lot of different things I could play with right here with the sinker, but I believe the sinker is a perfect example of actually being in that optimal window for increasing things like horizontal break. However, again, you can try to optimize something else, such as spin rate. If I wanted to increase my vertical break, there's a different window for that. So this all has to do with horizontal break because it's tailored to me as a pitcher. But I believe we can apply this to a lot of different pitchers and kind of solve their issues.
Cool. All right. Thank you very much.
Thank you.
Okay. Okay, so again, good morning, everyone. My name is Cadet Ross, Cadet Lowe, Cadet Treese, and Cadet Tallman. We're going to brief you on our contributions to the combat survivability study. So take a minute to look over our agenda. Firstly, I'd like to say thank you to DTRA, the Defense Threat Reduction Agency. They're our sponsors for this, and they've made everything possible for what we've been able to look at, what we've been able to do. So without further ado, what we've been charged with is developing a complex or a computational software designed to calculate the combat strength of a formation after a nuclear detonation. We're focusing on the Armored Brigade Combat Team because it's the most survivable formation. It is essentially the biggest formation for mounted warfare, and it's what the Army has labeled as most important for this project. The most important part for this is to make it simple, especially for commanders and their staffs, because the idea is that this will be given to individuals that don't have a background in nuclear engineering or health physics. Most importantly, it's going to have a graphics user interface that is exceedingly simple to use and very intuitive. And essentially taking like the complex graphs or graphs from Glasson and Dolan, Effects of Nuclear Weapons textbook, and then converting it into a digital format. As for current gaps in research, essentially the Army has a good idea of what happens to personnel and what happens to equipment. However, they do not have a method for applying this knowledge to formations expeditiously. Currently, it takes quite a long time to actually do an analysis of, how it would affect like personnel or equipment. The purpose of this is to make it far quicker and readily available for commanders. Lastly, we're especially focusing on the aspects of combat power and identifying and mitigating critical vulnerabilities in post-nuclear environments.
All right, so for our model introduction, we're doing surface level blasts, and the thermal and blast effects are going to be most prominent in this region. So the commander's going to input three things. He's going to input the location of the friendly units, the location of the weapons, and then the yield of the weapon. Again, it's going to be a planning tool for commanders to evaluate different avenues of approach and find the most optimal avenue of approach when they realize that a nuclear weapon is a threat. And then we use MATLAB as our code to integrate the nuclear weapons effects equation like you see down here into the graphic user interface. Slide, please. All right, so for our assumptions, the first assumption we have are about the detonation. So again, surface level, and we're not accounting for prompt or residual radiation. The reason we're not accounting for prompt radiation is because in the region where prompt radiation is going to be an issue, the thermal and blast effects are dominating that. And we do not account for residual radiation because that's just outside the scope of our code right now. For environmental assumptions, we're doing flat terrain and uniform atmospheric conditions. So we're not accounting for wind speed or weather, and we're not accounting for fallout. For our unit assumptions, the entire Armored Brigade combat team is going to be within the 20 square kilometer grid, and all vehicles are going to be buttoned up. It's going to be no soft targets or like soldiers outside of the vehicles. Slide, please. All right, so this graph is broken up into left and right. So on the left, we have the overpressure effects, and on the right, we have the thermal effects. So at about 45 plus PSI, we're looking at overturning the heavily armored vehicle and killing the crew inside, and that's going to be 0% combat effectiveness. And then down at the bottom, we have 1 to 5 PSI, light external damage. They're still mostly mission capable, so they're going to be about 98% combat effective. On the right, we have 80 plus calories per centimeter squared of thermal fluence. It's going to be catastrophic burns to the crew, resulting most likely in death. That's going to be 0% combat effectiveness. Then down here at the bottom, we have 1 to 10 calories per centimeter squared of thermal fluence. Looking at minor external damage, but it's going to be combat effective with 99%. Then we have the entire gradient in between. This is what you can code. Next slide, please. Right here, we have a Bradley infantry fighting vehicle. You can see all the sensors and everything that might be affected by thermal or blast effects.
Okay, so under the hood of our program, on the left, you can see our graphs for peak overpressure. On the right, you can see our thermal fluence. This is taken from the Effects of Nuclear Weapons textbook from by Glasson and Dolan. On the bottom, you can see our approximations for that. The way that we did it is we plotted individual points from the graph into generative AI, and then we utilize that to curve fit a piecewise function that follows that curve exactly. As for the thermal fluence, I've only included the 3 calorie per centimeter curve for the sake of the presentation. However, in our model, we have accounted for all 6 curves.
Now I'm going to orient you to our graphical user interface. So if you look to your top left, you're going to see the yield input. This ranges from 5 to 100 kilotons in 5 kiloton increments. Under that, you're going to see our blast effects. This will be represented in overpressure in pounds per square inch. And then moving to your right, you'll see the thermal effects, which are represented in thermal fluence and calories per centimeter squared. And then the furthest right, you'll see our battalion effects. And this is where we're going to show how the weapons degrade the individual nuclear battalions. In our current scenario, we have an Armored Brigade combat team divided into 3 maneuver battalions, and they're currently tasked to seize objective Eagles, which is in the far north. They're moving north along a main supply route, which is currently I-29, located in eastern North Dakota. And our commander is assuming that nuclear weapons are not in play. So we're looking at this from the top down. Let's zoom in. This is a picture of Thunder Run, which I'm sure we're all familiar with, and it's an example of what tanks moving along a main supply route looks like. Now, we've assessed that a nuclear weapon is going to be detonated along the main intersection of I-29. And if you look to the blast effects, you can see that our innermost ring, which is the red, is going to be represented in 200 PSI. And then our purple ring, which is the outer, is 1 PSI. And then our thermal fluence, which is on the right, is going to be represented ranging from 3 calories per centimeter squared on the outside, which is the yellow ring, to 50 calories per centimeter squared on the inside, which is the red ring. Now, looking at our battalion effects, our first battalion, which is the furthest north, has sustained 1.94 PSI of overpressure and 5 calories per centimeter squared
thermal fluence, and we're assessing them at 98% combat effectiveness. We're saying they have full mobility and then minor external damage. Our second battalion, which is under south of first battalion, is sustained 29.87 pounds per square inch of overpressure and 50 calories per centimeter squared of thermal fluence. And we're saying they're at 30% combat effectiveness, that they have external systems destroyed, vehicles are immobilized, and severe damage. And now our third battalion has sustained 7.84 pounds per square inch of overpressure and 25 calories per centimeter squared of thermal fluence. We're saying they're at 90% combat effectiveness and that they have moderate external damage and near full mobility. Now, using our tool, our commander can account for the effects of nuclear weapons. In his or her area of operations, he or she can give his maneuver battalions left and right limits. Now, as our maneuver battalions process north to seize objective eagles again, a nuclear weapon is again detonated at the same location. And then you can see that our first and third battalions, which are the furthest east and west, are now completely outside of the blast and thermal rings. Now, this means that they have 0 overpressure, 0 pounds per square inch of overpressure, and 0 calories per centimeter squared on their thermal fluence. However, our second battalion is located in the same location because of the conventional constraints of this warfare. Now, comparing our first scenario and our second scenario. In our first scenario, we had 65 tanks that were completely combat effective. And then our second scenario, we had 69 tanks that were completely combat effective. And 4 tanks might not seem like a lot, but 4 tanks also can be the difference between seizing an objective and not seizing an objective. Now, using our tool, our commander can account for nuclear weapons in his or her planning and can continue a mission after a nuclear detonation.
All right, so looking forward, there's essentially 3 areas that we can improve upon to make it more useful for commanders and more accurate. First, we're going to increase the mission complexity. This includes accounting for multiple or staggered nuclear detonations on the battlefield, as well as different unit dispersions and types within the AO. Second, we're going to need to increase the complexity of radiation effects. So finding the effects of radiation is going to include accounting for prompt gamma and neutron doses on soldiers. And then also we're going to need to expand the model to include radiation sickness models, cumulative dose tracking for units, and then fallout dispersion models, which are going to become important as units continue to fight on the nuclear battlefield. And then finally, we're going to increase the environmental complexity. So specifically for fallout, we're going to need to include wind speed and direction, and then also geographical and 3D terrain effects. So to conclude, we've created a tool that turns complex technical information into simple, actionable results for commanders. It enables commanders to rapidly make decisions about planning, whereas otherwise they would have had to guess, made educated assumptions that might take time. Our tool demonstrates the feasibility of integrating nuclear effects into tactical decision tools that require 0 to little expertise to use. And then finally, we've identified some gaps. Any questions?
To estimate the yield of nuclear weapons. So currently this is a planning tool. So what they would have is they would have some sort of intelligence saying this is the nuclear weapon that could be in play in the scenario. So then they're going to use that in the planning tool to assess how far they need to space out their battalions. Thank you. Yes, sir.
How long does it take to run one simulation computer one scenario?
One simulation takes, so you input the 3 clicks, which are the locations of the nuclear battalions, and then the strike and the yield. And then it takes approximately 5 seconds to do the entire computation. Yes.
Are you able to incorporate like any special equipment, like if the data has extra like column equipment or something, like if the damage effects on those?
So not right now, that's something we're working on.
But what resources are you constrained by? If you had a magic pen, what resources would you allocate to this specific model? If you just need to make sure.
The ability to quickly model terrain, how it affects like the blast effects. That's the hardest part of any model. Modeling blast is like mountain ranges.
The 3D terrain, just to expand upon that, is not accounted for in most of the weapon like effects models. It's just, it's very complicated and it's going to be very computationally taxing. So as computers get better at that, it'll probably be something that we look into, but it's not something we're looking into right.
So how does the commander get the yield to put in to get the result?
That's what we were talking about earlier. Since this is a planning tool, it's most likely to be something from intelligence, okay, the enemy, like we had 20 kiloton weapons. Other questions?
So making the assumption for people outside of the vehicle, assume this is all assumed in the vehicle, but, you know, traffic, air, people outside the vehicle, maintenance, things like that.
Yes, sir. In a scenario like this, anybody that is outside of the vehicle will sustain much heavier effects from the weapon themselves. But for the purposes of like a mounted formation, assuming that they're buttoned up ensures like maximum survivability of the formation. So if you already know you're entering a nuclear, a situation where a nuclear weapon could be in play, you keep your formation buttoned up inside the tanks as you.
Discussion, any other questions?
You modeled a certain spot, you looked at different bursts.
Not yet, sir. We didn't put heights of burst in this model yet. I think part of the reason we did that is because we're trying to keep it simple to a commander's perspective, and a commander might not necessarily understand the relevance that height of burst has.
Very good. Thank you.
Presentation is on analysis of private fusion companies for DoD partnership and the defense application. So the motivation for doing this study, research, was the fusion industry is becoming more and more saturated as breakthroughs are made, and I believe we near nuclear fusion energy. And the goal is to inform the DoD on fusion companies that are worth focusing on and worth investing in and partnering with as we go towards this goal. This is done under the umbrella of Fusion for National Security, which is an informal group of heads and experts in the fusion community, as well as members of the DoD who meet monthly to discuss fusion energy, do presentations, and talk about the same thing that I'm talking about, which is applications of fusion energy and fusion technology to the Department of Defense. Overview of this research. So this research aims to, as I said, inform the DoD of fusion companies that are worth investing in and focusing on through the viability of that specific company achieving fusion energy, supplementary technologies being developed by that company, and the defense applications of both of these kinds of technology. And the end goal is to create a sort of standardized metric for the DoD to evaluate fusion companies. Methodologies, how this was done. The first step was to get a diverse group of pilot companies to be evaluated to represent the broad scope of different fusion approaches and the different companies involved in nuclear fusion. And these were the companies selected. The next was to standardize evaluation criteria. So there's a broad variety of fusion approaches and fusion companies. Standardizing that through a challenge, the most helpful criteria is determined to be the Lawson criteria, the product of plasma density, ion temperatures, and confinement time. Facilities were also evaluated based on NASA's technology readiness levels, which are used to evaluate emerging technologies based on maturity and readiness to be deployed in an operational environment. Step was research and assessment. So companies were evaluated based on their lossing criteria and put on this graph. They're compared to others in the community, and then the National Ignition Facility, which has achieved above break-even fusion, or above break-even energy output. Also, an important part of this evaluation was supplementary technologies being developed by these companies. Almost all of these companies have been forced in some way to develop technology on their own to meet with the extreme requirements of achieving nuclear fusion. Those technologies provide their own benefit to the DoD outside of nuclear fusion. Things like superconducting, high temperature superconducting magnets, laser technology development, and even things like novel use of AI, as well as many other things. So evaluating these supplementary technologies on top of the fusion energy likelihood of these companies provides additional benefits to the DoD, even if said company may not achieve nuclear fusion. Then determining potential defense applications of the fusion energy technology as well as the supplementary technology being developed. Things like ZAP Energy's Z-pinch technology used in things like modular nuclear reactors, avoiding many of the pitfalls that are seen with fission nuclear reactors, such as the intense irradiation once those reactors are turned on, and battlefield proliferation concerns and irradiation concerns. ARC, like Commonwealth Fusion Systems, is possibly a replacement for the nuclear reactors aboard aircraft carriers and nuclear submarines, providing less highly enriched fuel required and possibly the ability to harvest hydrogen isotopes. Laser technology has many defense applications, such as direct energy system, weapon systems, as well as detection systems and radar like high temperature superconductors used for EMALS, electromagnetic launch systems, for things such as fighter jets, and many other defense applications. Next, final step was to get all of these factors and use them to evaluate fusion companies on a standardized scorecard. So how was the culmination of these things, bringing them together, displaying criteria, and then evaluating them on a easy to digest scorecard that the DoD can use to evaluate these companies. It's worth noting, this is a very infantile, say, scorecard, something that in future research, we focus on breaking down these specific criteria more and more in order to develop a more useful, more applicable, and a more solid scorecard. So this is the direction that this research is. Kind of conclusions is that fusion development is huge for the DoD, both in the creation of fusion energy and the supplemental technologies being developed. It is important for the DoD to focus on these things and to capture technologies being developed in the fusion industry for applications. Even failures of fusion companies that may not achieve nuclear fusion energy have massive benefits to the DoD if their supplementary technologies that are being developed are of use to the DoD. Future work and limitations to this research. In the future, as I said, developing the scorecard more, getting more in depth on quantitative and calculating the scores for these things. And we are limited somewhat in our existence as a military academy and working privately with companies, but developing CRADAs and agreements with other companies and getting more involved. Almost all of this was done based on open source information. Being able to work with those companies will provide a better insight for evaluating them and getting more useful information for ranking and scoring. Thank you.
Questions?
Something like this, Eli, could be used to like, based on the feasibility of like a technology or something, would be used to like allocate like federal funding, or is it more so just to like add technologies to keep our eye on?
Yes, I think definitely federal funding. The DOE especially has massive grants that they give to fusion companies. And something like this, I know the DOE has their own system, but the development of a standardized scorecard like this definitely help in allocating the funds. You're seeing more and more money being put into fusion. And yes, definitely, and as well as defense partnerships and who we are focusing on when we are buying things like superconductors for this particular.
So you mentioned that the DOE also has their own like system for this. Would you imagine the system, like, does it open to some of the same sources, like to make it easier, or are you imagining it as like completely separate?
I think that it has very different goals. The DOE is focused on production of fusion energy almost exclusively. And this is focused on very much how this benefits the DOD. So fusion energy in general does benefit the DOD. Application of fusion technology, fusion energy on bases. But I think specifically looking at specific applications such as modular reactors or the supplementary technology is not like an afterthought on this. It's a very important part of why the DoD would choose to partner with specific fusion company. So I think different angles.
So I suspect of those 50 companies that you alluded to at the very beginning, so 50 or so in the country, I suspect that most of those companies have generated a lot more PowerPoint than they have plasma. And as if I were a program manager with money to invest, one of the first questions that I would have is which of these companies are making tangible progress and which ones are selling stable? Which ones are just basically making crap up to get federal funding? What is the analysis you've done so far? Does it have a way to kind of try to answer that question, to differentiate the ones smelling snake oil from the ones making profits?
Yes, sir. The standardized scorecard that we have doesn't have necessarily a section in it for that. It was originally part of this, and then I don't think there is a solid kind of standardized way of dealing with that. I think that would definitely be something worth tacking on to this to more comprehensively review these. I think part of what the DOE is doing is they're granting initial funds, and then the companies have to meet specific milestones. So I think rather than reinvent the wheel, that was part of the pilot companies chosen is if a fusion company hasn't produced anything, it's just concept, physics haven't been validated, then it's not even worth doing an in-depth analysis if they haven't done anything involved. Yes, sir.
If I could add to that answer, great answer. This is private money that's going in, and they expect results. And so there are massive expenditures going into things like power storage and capacitor systems and switching and so on. And so they are experimentally driven in a great extent. Yes, there are some who are just power pointers, and as Elijah mentioned, is working. But there's a good number who are, like, if you look at Malaga, Washington, where there's this enormous accelerator being built to accelerate. I think the prediction is they're going to fail, but there may be some amazing technologies that they've developed in order to create these thriving plasmas that the DOW might be able to leverage. So
I agree. I think an important part of this is rather than have the DoD developing these technologies, these private companies, they have their own motivation for doing this. So let them create or fail in this technology. And then rather than spending billions of DoD money, you can come in after the technology has been successfully validated. It's a benefit.
Are you planning on continuing this work next year?
Likely, sir. I'm not sure what my capstone requirements will be, but
Yeah, if you do, there's a captain coming into this department, he had some brain stout. He did something very similar to this, but his PhD work was on selection methodology for a future modular reactor. I see a lot of overlap in your work with his. So I highly suggest that we continue this. Captain Brent Stout, when he shows up this summer after he's gotten settled from the fall, if you want to continue this, I will talk to him because I think you could learn a lot from the way that he lays out in his PhD dissertation how he developed the selection criteria for modular reactors and how you're saying this is how we should select partners of interest for fusion.
thank you.
Good morning, everybody. I'm Jake Truckman.
I'm Diesel Wash.
I'm John Mathis.
Hector Seabass.
Zach White.
I'm Will Cooper.
Good morning. Welcome to our presentation on radiation effects on gallium nitride semiconductors. So firstly, to jump in, we're going to get into an introduction, how semiconductors work, the mechanisms of damage we expect to see on these semiconductors from radiation, how we selected the component that we're going to model and test, future work on that testing, and then how it applies to military and its significance. So firstly, what is a gallium nitride semiconductor? So gallium nitride semiconductor, or GaN semiconductor, is a wideband semiconductor often used in military, aerospace, and nuclear applications. It is for that. It is used because that wideband quality makes it very responsive. So you can very quickly turn it on, turn it off. It's rad hardened and as its own quality. So they're very sought after in those applications. So it's very important that we know how to react in a radiation environment because they're going to become, I think, increasingly more important, whether it be in space or, God forbid, a man-made environment. I have an example up here in the top right that shows you an example of a camera looking at the sun during a solar storm. And so you can see the effect of that radiation on that camera, all those pixels going out. And I think it's also worth noting that that S4 is not even the worst solar storm that can happen. So despite our reliance on these semiconductors, the effects of radiation on these gallium nitride transistors is not actually that well known, which is what we're going to get at here. So for our objective on this project is to be able to characterize that image.
So just for an overview on how semiconductors work, so essentially you take a material and you dope it with either an electron acceptor or a donor. And this creates N regions where there's extra electrons or P regions where there's like holes for these electrons. This contrast allows electrons to move or create current. But when you're in between these two regions, like kind of like right here, you get what's called a depletion barrier, which is where the electron fills these holes and that blocks current. However, if you take a gate and you apply a voltage, you can get these electrons to overcome that depletion barrier and restore current. And so since you can control current, you can also control like binary output. And so just an analogy to think about this, I kind of like to think about it like cadets at a brief. So at first you show up and all the cadets are kind of in the back, right? And there's that forward line where no one's really crossing. So where the cadets are, that's kind of like that end region. Then when there aren't any cadets, it's like that P region where there's electron holes. And that like four lines, that's like the depletion. So right now, no one's really moving. Everyone's kind of in the back, away from the stage. Until you get someone that comes up, and they yell at everyone to like move up, right, move forward. That's like your gate applying a voltage. And then people start moving forward past that forward line of advance. And then you got current flow, you got control.
So the three main mechanisms which we understand that charged particles can influence a semiconductor are transients, burnouts, and single event upsets. So transients is just whenever the charged particle interacts with the surface of the semiconductor and then it deposits both a charge and then also in the creation of more electron hole pairs, it then creates heat. Which can initially result in just a simple fluctuation in current and voltage. Moving on, to like a more severe particle interaction, it can then also like generate enough heat to create a burnout, which is a permanent, which can like permanently change the lattice structure of the semiconductor. You can also have single event upsets, which can essentially flip a 1 to 0 and cause the semiconductor to open or close. But single event upsets don't permanently damage the semiconductor as much as they say burnout, which can turn it into a full, which can effectively make the semiconductor a conductor and remove its ability to open and close altogether.
Additional mechanisms that we're going to be looking out for is something called a gate rupture. So basically, when the particle comes through, it could create those ion fold pairs as well as displace some of the atoms. Just going over a few of the finer details, skipping over a few details. What this basically does is it can form a conductive path through the gate that the electrons can cross through or tunnel through. So basically, you lose the ability to turn off that gate. There's always going to be some amount of current leaking through it. You can also get current leakage without a gate rupture. Again, this is sort of a similar mechanism whereby these electron hole pairs get formed, and that will cause basically a spike in the local electric field. And again, this has to do with a little bit of quantum physics, but basically that increases the probability of quantum tunneling. You also get displacement damage, which knocks out the lattice structure. That can create energy traps for those electrons. It basically makes tunneling more likely. It's called trap-assisted tunneling because electrons can jump in and out of these traps to be able to tunnel. The final thing that we're going to be looking forward to is resistivity changes. We're more so looking for long-term resistivity changes. And this is mostly caused by, again, some of that displacement damage. If you want to think about it like making the road for these electrons across a little bumpier, so it's harder for them to move, and that therefore is basically increasing the resistance of the semiconductor.
All right, so next we're going to be talking about military applications of our research. So semiconductors are pretty much the backbone of a lot of modern day technology that we have, especially when it comes to military applications. So for example, semiconductors are used in missile guidance systems, telecommunications, GPS surveillance, any technology that the military uses, you name it, semiconductors are involved. And what we want to do is we want to understand how radiation is going to affect the reliability and survivability of these systems. For example, if we have a nuclear detonation in the atmosphere and we want to launch a nuclear missile towards an intended target, we want to make sure that our missile guidance system in our nuclear weapon is still functional after going through a heavily radiological environment. So basic mechanisms of hardening that have already kind of been developed are shielding. So what kind of shielding you have, or external shielding outside of any semiconductor materials that you might have, material components of your actual semiconductors, and then your component selection or the type of transistors you have. So that can be either oxide or versus mitigated oxide. And then as you can see, here's some applications of semiconductors. So you have your GPS satellites. You also have here is your Minuteman III nuclear missile. And so the guidance system that these things use heavily rely upon semiconductors. So we want to make sure that our semiconductors actually work and survive in nuclear environments.
So now looking into kind of specific component selection here, we're looking at our gallium nitride, which is kind of our novel option, versus silicon MOSFET, which is just kind of traditional, tried and true, what we know works just in all sorts of electronic components. Talking about what Hector was just hitting on, if you compare the two right here, the gallium nitride is on top, silicon MOSFET's on the bottom. The silicon MOSFET has this metal oxide insulator right underneath the gate, whereas the gallium nitride has a different layer. It's not an oxide, it's just an aluminum gallium nitride layer. That simple switch of materials there, leads to what Chase was talking about. That metal oxide is much more likely to be ionized when you have high energy particles moving through, whether that's an alpha or a high energy proton or neutron. And so by just switching that material and having aluminum gallium nitride instead, you're much less likely to have a gate rupture. Secondly, the high displacement energy of gallium nitride, as Chase talked about with the bumpy road analogy, you can think about like a semiconductor as just like a big grid or a matrix, right? And so
Your silicon option is just a bunch of silicons lined up in a lattice, kind of like a diamond. Or gallium nitride is the same, but it's just gallium nitride. If you then subject that to some sort of radiation flux, you have all these high energy particles running through, bumping into all of these. The silicon bonds in a silicon MOSFET are a lot weaker than the gallium nitride ones. And so lower energy particles are going to be able to knock those out and essentially, like Jason's talking about, create like a pothole in your road. And especially with the way that transistors work, as you're applying current across that, the electrons are essentially going to get stuck in that pothole, and they're going to sit there, and that's going to increase the amount of voltage that you need to apply to switch your transistor from a 0 to 1.
So now if we look at the actual computational modeling of it, right, we know the general layout of the semiconductor, but now it's important to actually look at, okay, what does this look like digitally? So we initially started utilizing Silico, which is a TCAD software that's used to design and model semiconductor devices. So for us, we're working with the EPC 2019 in conjunction with Sandia National Labs. They're very interested in the defense application of this, so we want to model that. We then proceeded to duplicating the layout here into SRIM, which is stopping the range of ions in materials, which allows us to simulate charged particle interactions that will come from a radiation incident into the actual semiconductor. We model it between 4 and 5.1 MeV because we plan to model this with the Houston particle accelerator, which operates that bandwidth. And what we're interested in, as we've talked about, is if there's electron hole pairs are displaced, that will cause major disruptions of the semiconductor. When evaluating between these two energy bands, we found the highest probability and highest rate of ion displacements that occurred at 4.7 MeV and ended up being 1314 ion 1314 electrons being displaced per ion, which is the local maximum in each region of it. We can also look through and see the penetration depth of the alphas goes all the way through. But as we see that greater deflection, it's important to understand how that's affecting those hole pairs. Essentially, we could end up with an incident where we have way too many hole pairs, and part of it causing those disruptions that we talked about with magnetization damage. So it's very important also to understand that that energy operating for those alpha particles plays a big difference. If you increase that energy too much, we end up with less kinetic energy transfer, less ion displacement, or on the other side, too low energy, and then we don't get much ion displacement.
So regarding our future work, we plan to enter the experimental stage in our research by next fall, so AY27. Our current experiment that we designed is we're going to bombard our semiconductor with alpha particles. We're also going to be placing a 200 volts through our semiconductor, so our semiconductor will be on and running while it's being bombarded with alpha particles. Again, this will take place in the Houston Particle Accelerator located in Portland basement. We're going to be mainly examining flux distribution of the alpha particles through our semiconductor, and we're also going to be looking at energy deposition and displacement within the semiconductor to kind of test our functionality and survivability of our actual component during our simulated radiological event. Concludes our brief. Any questions?
Like hardening against radiation, something that companies are already able to do on a mass level?
So the selection is the main idea right now. So we talked a lot about like the GaN semiconductor type, but you can also use like the MOSFETs, like low reference, like the metal oxide semiconductor field effective transistors. So they all have different applications, but what we want to see is like which is most ideal to inform. There's a lot of like information on the semiconductors, but what hasn't been covered is like those damage mechanisms affecting the functionality of the semiconductors, which is what our research is getting after, so they can determine like the most effective components to use.
Shielding ain't too complicated, but the problem is like trying to figure out how much you really need, right? Because if you want to send something up into space, you want to make that as light as possible, right? And so having a like lead shielding on everything isn't an option, right? So you got to pick and choose where you're going to put that shielding, what you're going to use.
You have a view, how prevalent are gallium nitride semiconductors? Are they readily available or is it a specialized technology?
They are readily available, so the component that we're using, it's $2. So we can use a lot of them, we can buy a lot of them.
It's enhancement mode gallium nitride. That's what's newer tech that they're specifically looking at. So it's set to off. And then when it needs to be on, then it will be on for whatever circuit usage you have. That's relatively new, 10-year tech. So it's not well characterized. It's an open question.
And they're a little bit more expensive even at $2 than if you could buy silicon MOSFETs in bulk. But even now, though it is a little bit more expensive because it saves you weight and space when you're trying to put something in space or just in sort of aerospace application. Like it can save you a lot of money on fuel. It just
You might not like it, but I'm gonna ask it. So, we focus on gallium nitride, also material. Gallium nitride being a wide bandgap semiconductor generally is not used for digital logic. It's kind of not a thing, sort of. So things like signal and upsets are kind of irrelevant unless you're doing digital logic. And you also referenced the Minuteman missile system, the guidance system in that, which I assume was probably designed in the 1970s or something like that, before gallium nitride was a thing. So why look at gallium nitride? Why is that what we chose?
I was gonna say, so regarding nuclear weapons, America does not make any new nuclear weapons due to treaties. But that does not necessarily mean that, consider what our enemies are upgrading.
To the gallium nitride point, sir, it's been shown to be more resistant generally towards radiation out of the available types. Obviously, like our point is to try to fill some of that gap with the information with the enhanced MOSFETs, but it isn't really shown right now. So we want to determine is, can we use this as a baseline to inform on potentially more beneficial or other types of semiconductors that their resistances. What we're going to do with this is essentially validate that the models can work for a type of semiconductor, and then see if we can increase that application to help with component selection and other things.
Great. And to address the point about the Medevac missile, I apologize if I made it unclear. I wasn't trying to say that we use gallium nitride semiconductors in the Medevac missile. I was kind of used as a general application for semiconductors in military technology. So I apologize if I made that unclear. Very good.
Questions? Well, let's thank our team again.
Good morning, everyone. I'm Cadet Michael Marcigliano, and I'm going to tell you about my research into a cross-count study of Yttrium-89 activation for 14.1 MeV neutron dosimetry. This research was conducted in collaboration with San Diego laboratories, and the goal of this project is to evaluate the feasibility of Yttrium-89 being able to be used as a complementary or alternative dosimetry material used for measuring high-energy neutron flux. Here's the agenda we'll go over. Okay. So why do we care about measuring high energy neutrons? High energy neutrons, as in 14.1 MeV neutrons, are critical in military and defense applications. It's really important in understanding these neutron fluxes allows us to better understand our nuclear weapons, physics and engineering, the radiation effects it might have on our systems, and also allows us to help develop fusion-based energy systems. And then uncertainty in these neutron measurements is what can directly impact mission planning and system reliability. So the goal of using Yttrium-89 or something else may allow us to maybe lower uncertainty in the future. So the problem. Fusion environments. So the fusion environments can produce 14.1 MeV neutrons using DT fusion reaction, deuterium and tritium, being smashed together, whether it's deuterium into a tritium target or at the Omega facility in the University of Rochester, there's a DT pellet that is shot by lasers and it creates the DT reaction. And then you get 14.1 MeV neutrons. However, these really fast neutrons are extremely difficult to measure. and detect directly. So there's real-time detection systems. These are active detectors and it requires power, calibration, and like live monitoring. Instead, what's often used and what they use at Sandia is passive dosimetry systems. These passive dosimetry systems allow us to get this neutron flux over time and allow us to analyze after the experiment happens. So if you think there's a high energy neutron, like you're not gonna have people in there, it's harder to have equipment in there, but there's 14.1 MeV neutrons coming. So instead, you use this passive dosimetry where you place an element inside this environment, and then based on its transmutation to a different isotope, will allow you to read the radiation, and depending on how much radiation and counts that you get, you're able to say how much neutron flux there was. Right now, the current dosimetry standard is niobium-93 activation. There's an N2N reaction that occurs. It turns it into niobium-93, which is a metastable isotope. This metastable isotope emits gamma rays, and then those gamma rays are then measured, and then that measurement is tells us the neutron flux in that environment. Limitations of niobium. So why are we even trying to do yttrium? What's wrong with niobium? Currently, there's nothing wrong with niobium. Produces uncertainty measurements of around 5%, which is pretty good, which is okay. But it's a single observable channel. So there's an N2N reaction, and then you're reading the gammas off of it, then that's it. So you're using gamma spectroscopy, and then that's the only like measurement that you're taking on this niobium isotope. It's more sensitive at moderate fluence also, but it's less advantageous at the higher neutron energies. So if you have anything higher than 14.1 MeV neutron, which has been seen in these high energy facilities. Yttrium-89. There's 3 reactions that we're looking at. The N2N reaction is the gamma emitter, so we're less thinking about that because we already have gamma emissions from that's niobium reaction. And then there's the NP reaction and the N-alpha reaction, both which turn into beta emitters. This allows us to measure both gammas from our niobium and also the beta counts from yttrium. This allows multiple observables. So if you think like we're using the gamma counts from niobium in tandem with the beta counts that we're getting from this yttrium, allows this yttrium to maybe be used as a complementary for niobium. It's also important to know beta counting is not inherently less uncertain than gamma counting, but it's what using it together may allow us to lower. Here's the experimental setup that I came up with at Sandia. It shows the foils that were used. So we have yttrium, niobium, nickel, and sulfur. Yttrium and niobium are both used. That just allows us to directly compare our results. And then nickel and sulfur are also included on the packs because of backscattering. So it's nickel and sulfur more react to moderate and lower energy neutrons, and including that in the pack allows us to measure that as well. It was irradiated at the Omega facility in the University of Rochester, which produces a 14.1 MeV neutrons. And then the post-irradiation counting the gamma spectroscopy is done using HPGE detectors. The beta counting is done using a scintillation detector or proportional counter. And this enables taking the results from the HPGE detector and the results from our scintillation detectors. We're able to compare beta counts and our gamma counts. I started this project at Sandia. So I showed up to Sandia National Laboratories. I wanted to pick up research. They came to me with this project, this one measurement. So they had previously put yttrium-89 into one high energy neutron facility before I picked up the project. And it showed that there was activation. And then I offered them to lead and take over this project because they didn't have the effort and resources to take it at Sandia at the time. So I took it over. And since then, we put yttrium in 2 more high energy neutron facilities. And while at Sandia, I constructed the foils that was used on the first trip. We placed them at the ion beam laboratory. Which you can see in the image on the right, demonstrate that it's at the ion beam laboratory, and the dosimetry pad, which is shown on the left, is placed directly into the target. That's where deuterium is sent into a tritium target to create your 14.1 MeV neutrons. And then now my goal is now to help evaluate the visibility of yttrium after lots of research into reaction channels and detectors. Okay, next I'm going to go more into the reaction channels of the yttrium-89. So the NP reaction goes into strontium-89, which is one of the beta emitters I was talking about, and it's a 1.5 MeV beta, and strontium-89 has a 50-day, about a 50-day half-life. Yttrium-89 is an end-to-end end-to-end to yttrium-88. It's the gamma emitter one, so we're less worried about that. We're focusing on the betas. That has a long half-life. And then the N-alpha reaction to rubidium-86 is also a beta emitter with a 1.8 MeV beta, and that has a half-life of about 18 days. And the problem that we run into is that there's two betas that are similar energies that can overlap during the counts. So it creates instead of just one massive amount of lots of betas, when we really want to just separate it. So we want to see our 1.5 MeV, we want to see our 1.8 MeV. And so to get past that, one of the things that was brought up is we can wait 3 half-lives of that rubidium-86. So we take rubidium-86, it's an 18-day half-life, we wait 3, so 18 times 3, about 50 days. We'll wait past that and then do our beta counts. Will then allow us to focus specifically on that 1.8 MeV beta from the strontium-89, which will help our uncertainty in the counts. This makes like the timing critical. So like that's one of the things that we're looking into is like when's the best time to actually start counting, and then that's one of the applications or one of the processes that we came up with. Okay, so Omega results. So there's been 2 campaigns at Omega, like I mentioned, led by me, and we went once in 2025 where our counts were too low and it was inconclusive, which already was off to a bad start, and then we had to change the pack design. So if you look at this image, it's a different pack design, same material, same elements on there. Zirconium instead of sulfur is on there now. And then it's done in a way so that the left side of a pack and the right side of a pack are identical. So then it can be ripped in half, and we can have half of it here at West Point and bring half of it to Sandia. And that allows us to compare our counts here at West Point to the counts at Sandia, which then also like helps us validate like the counts that are being done. And then now over spring break, more packs were put at Omega in April, and now the goal of this is to get the statistically significant counts that we want. It allows us to get enough counts so that we can then compare our data for that analysis. The expected outcome and conclusion. Niobium still currently remains like a strong standard for passive neutron dosimetry. However, if yttrium is successful, so depending on our counts that we get back from this April 2026 trip, the multiple reaction channels that it offers with the ability to cross-check the measurements, so taking the beta and the gammas, will hopefully allow it to be a complementary like usage with niobium to like better lower uncertainty of the neutron flux in these high neutron energy facilities. It may not completely replace niobium, but it's okay. Like ongoing results will tell us like the usage of yttrium. So the future of this project now is getting the counts from the April trip, and then taking that and using the data analysis to find when the best time to start counting the yttrium will be, and when if it can be used with them. Thank you all for listening. This concludes my brief.
It's 12:30, right?
Yes.
Okay, we have 57 minutes for questions.
You mentioned doing like stuff here. What are you doing here to get the fast neutrons characteristic of the DTG?
So what we did, like here, I haven't done like any specific stuff. So we built packs at Sandia, and then used those packs at the facility at the University of Rochester. And then the goal is that once we get those packs back from the April trip, we're gonna get them. They're getting shipped right now to West Point. Once we get it back through the gate into Bartlett Hall, me and Lieutenant Colonel will start doing counts, and then based on our counts, be able to do that analysis for that.
You mentioned that in like the second iteration of packs, you swapped one of them out for zirconium. Was there like a reason that you made that elemental swap?
They serve as similar. It's the backscattering. That's what you're trying to do.
Okay.
So
Yeah, I got a question about when you're doing the counts here to try to look at the betas and try to disentangle the the two different beta decays. Can you monitor that as a function of time to better separate those as well, rather than just, you know, picking it like at the 50-day mark, where a lot of the half-life has gone away? Can you actually watch them decay away? One of the beta channels?
I do not know the answer. to the question.
I can help with that answer. So we would have a gas proportional counter or maybe a liquid scintillation counter, and both of those are just not feasible to use over a very long time because you have to have gas flow in the proportional counter and LSC. You've got to physically count like up in a chamber. So
Gotcha.
it's not easy counting betas.
Gotcha.
Yes.
Okay. Thanks.
Questions?
I got one more. So you mentioned the three different reactions. You had a neutron to neutron. You had a neutron proton, neutron alpha.
N2N,
Yeah,
neutron.
what is the
proton.
N2N?
So the
What-
neutron hits the yttrium 89 and then two neutrons are.
Oh, and it's two neutrons. Okay, that's.
I liked your talk, so. You probably have found somewhere in your research, and I think you might have alluded to this a little bit better. The issue with neutron detection is discriminating the gammas from the neutrons. Like everything detects gammas and it detects. So what is it about, or is there anything about yttrium or any other bits of metal that you had on there that could help discriminate between neutrons coming from your DT fusion and gammas? Or is there nothing?
So for passive dosimetry, we're not actually directly measuring neutrons. It would be, we're just letting the neutrons hit our elements and then taking it outside of that facility however many days later, and then counting the radiation that comes off the new isotope that was made. So we're not worried about counting any neutrons. It's more just counting the actual radiation. So we're able to specify if we're counting for gamma, we use that HPGE detector. And then if we're going for beta, like liquid scintillation or portion counter. So that's how we're able to decipher between the gammas and betas, but neutrons are never actually being measured. It's just more like a back calculation to figure out neutron limits.
Thank you.
Yeah.
And for Signiano, what is something you learned about yourself while doing research?
That's something I learned about myself while doing research that can. It's probably like how much I'm capable of, because this was really like a big task for me to pick up at the time. I already felt like really like overworked and workloaded with like West Point stuff and schoolwork, and like it really helped me realize like I can really apply myself more to something I'm interested in, and like this is like the most amount of time and effort I put into something where like I feel proud of what I did. Like sometimes there's classes I don't really enjoy, but this is something I enjoyed doing. And I was like just really proud of myself after the fact, and like really showed me that like I can do more than I thought I could.
That's a good answer, Michael.
Great answer.
That's great.
Colonel Reinhardt, on your session chair for the third and final session today. We're going to hear from Team Aries, specifically about this year's project DEIMOS.
Thank you, ma'am. Good afternoon, everyone. I'm Cadet Matthew Pavia, and on behalf of our team lead, Cadet Nathan Chang, the team and I will be briefing you all over Project DEIMOS. So today we'll tell you a little about Aries and the problem that we seek to find a solution to, and then we'll dive deep into that solution, how we solve it with our launch vehicle, avionics recovery team, and our trainers. So the mission of Aries is to educate, train, and inspire cadets in space explorations, as well as finding new ways and developing them so that they can find new ways to expand on new technologies. The vision of Aries is to build a community dedicated to learning, dedicated to leading, dedicated to the process of expanding on what we once thought was possible. We first build this community by inspiring those that will come after us, because it is our job as future leaders to leave something behind for others to pick up and run. So Aries is the nebulous of this community because our influence goes on far beyond West Point. We work with middle school, high school, and university students throughout the year. We'll host launches where we teach them how to safely and efficiently conduct rocket launches. And this gives us an opportunity to spread our knowledge and love for rocketry. Aries does not define itself by the competition we compete in, the research that we do, nor the rocket that we built in it. We define ourselves and the impact that we have on the cadets, the Academy, West Point, and beyond. And finally, Ares is building the future of Army space operations through our research and the leadership that we bring to the table. So the problem that Ares seeks to solve is that what we're currently seeing in Ukraine is a very large problem with drones and UAS systems. So currently, those systems that the Army currently has as solutions to the drone problem are very costly and expensive. Ares seeks to find an inexpensive, easily deployable, and man-portable system that can solve that problem. So this is a multi-year project. This year, the goal was to just master the fundamentals. Can we make a rocket that has deployable airbrakes that can allow us to then build up in future years to take out an enemy drone? Next year, we'll focus on a more complex guidance system using more sensors and cameras to find and detect drones, as well as finding and using more control surfaces such as commands. And then in future years, we'll focus on high altitude launches and developing more of our capabilities. And I pass off to Cadet Rowan Stout.
Good afternoon, ladies and gentlemen. My name is Cadet Rowan Stout. I'm the launch vehicle team lead, and I'm here with my team, Cadet Coral Howell and Cadet Nathaniel Jang. And we're going to be going over our launch vehicle optimization. So for the launch vehicle, our mission statement is for the sub-team to build and optimize a launch vehicle to support Project DEIMOS and all of its scientific efforts. So this means implementing each subsystem's technologies into a fully optimized rocket. With research into launch vehicle material, fin shape, fin can design, and with launch simulations, we build the finished optimized rocket that we look to use for leading our mission. Looking through our design process, we started with our initial design research. So this is where we generate and come up with our critical design decisions based on the vision of Project DEIMOS. Here we fit the vision of each sub-team and each system together to create a final working optimized launch vehicle. And this is also where we do research with calculations, math, physics, and prove and disprove certain engineering and design decisions. Finally, using this initial design research, we are going to come up with our finalized design. So this is where we apply what we learned from our initial design research and kind of start to make this final launch vehicle. Here we use simulations to finally determine the small details that each portion of the rocket will be. So this is where we determine our radius or our length of our rocket, the weight, and all of this total, where each subsystem goes on the final launch vehicle. And finally, the biggest, and I find the most important portion of our design process is building and actually launching the rocket. So for our prototype here that you see laid out in front of me, this took about 25 man hours to build in total between the three of us. And this was the biggest hurdle in this process because you're designing something completely from scratch. We have used no off-the-shelf materials except for a couple of flight computers, but beyond that, we're making everything here in-house. And another thing that people often look over is the prep for launch day. There's a lot that goes into that, and that's something that's very costly and time costly especially. And finally, we have our full launch day where we go on Saturday and we launch and collect our data that validates our engineering decisions. Next, I'm going to hand it off to my teammate, Cadet Coral Howell, who's going to explain the materials analysis and those fin.
So in regard to material, as we talked about earlier, we really were looking at creating something that was cost effective. So we looked between blue tube, fiberglass, and aluminum. Now on the right side of the slide, you can see the different material properties, and these are what guided us in what we decided in our decision on aluminum. Now you can see that the Young's modulus for fiberglass and aluminum are both a lot higher than blue tube, which means they're less likely to undergo deformation. However, the bulk modulus for fiberglass is less than that of aluminum. That's ultimately why we chose aluminum, because it's more likely to deform than the material is to entirely fail like it would for fiberglass. Then I'm going to pass it off to Cadet Jing for.
Yeah, so further proving why aluminum is a successful material for this project, we go into, on the right side, we're going to talk about the shell mass. And one of the biggest differences between these three materials was the density of aluminum, which is a concern, especially for designing a rocket. You would think lighter is better. However, while aluminum is denser, it does have we are able to calculate the shell mass to be less than 5 kilograms, which is relatively light, and still able to be able to fly fairly well, especially being dense. So now going down to the heat of the drag force on the aluminum and how that is actually calculated. We start first with the power generated by aluminum. And we use a few assumptions in the bottom left, as you can see, as the density of the air be calculated as at sea level. And after that, we calculate that over a period of 10 seconds, simulate some flight time. And using that full energy, we calculate the temperature change and our next assumption, which is that energy is conserved. And using that assumption, we were able to find a temperature change that we finally used to determine the linear expansion of the aluminum throughout a launch, which ended up being less than 1 millimeter. And that comes to our last assumption, which is that the aluminum will be uniformly dissipated. So when it expands, it is uniform rather than some areas being expanding while others do not. And that is going back to what Rose.
And then moving on to our fin design. So there were a couple of important things about our finalized design. So that includes the number of fins, 4 fins, the tapered swept geometry, and the dimensions of the actual fin can itself. If you can see in the graph on the slide that compares stability and drag, this green line is the most optimized trade-off between the two, and all of the dots are simulated rocket launches created by a synthetic data set. All of this was created using the Garmin stability equations, the drag equation, and an equation for fin flutter. This allowed us to create these graphs which talk about this engineering performance ratio. This was created based on that green line that you saw in the previous graph. And it allowed us to decide a optimal number of fins, which was 4, and an optimal shape. If you see in the corner where the graph gets more yellow, it's when you have a decreased span and an increased taper ratio, which is what is seen with the tapered swept geometry. And then we also looked into the optimal suction side displacement thickness, chord length, and span, which were equivalent to that with the shape that we decided, and the suction side displacement thickness is the reason that we canted the edge of the fin can to ensure that the air that was moving around the fin can stayed close to the fin itself.
With all that being said, this is our final. With all that being said, this is our final design for our rocket engineering picture. So as you can see, we have the 3 different subsystems in green. Is the Project DEIMOS nose code, the Project DEIMOS guidance controls, and our avionics bed. With all of this coming together, you can see the diagram where each portion fits. So we have a Loki J396 motor, which is an American-made motor, and it has an impulse of 650 Newton seconds, which is a pretty high impulse for just a J-class motor. Anyone familiar with model rocketry will know that this is a pretty optimal motor, and this allows us to really get a good oomph off the launch pad heading into whatever. This gives us a good impulse to get off the launch pad and get to higher altitudes than what would normally be for a J motor. We also see that we have 2 points of separation. This is going to be important later for avionics recovery when they talk about their portions. But this is basically where the 2 different parachutes will come out in our recovery process. We also have energetics on the end of each side of the avionics bay, which later on avionics will also explain for the deployment of these parachutes. It's important to note here that we have the center of gravity and the center of pressure being the blue and red stars respectively. And this is important to be straddling the guidance controls because with the guidance, as you'll hear later, the center of pressure is very important for this. So here's a video of our launch. Once it heads up, you'll see the black smoke from the Loki motor. And this launch went all the way up to 2,500, or excuse me, this launch went up to 1,813 feet, which has air brakes deployed, opposed to our simulations that we ran, which had a 2,500 foot altitude with no air brakes deployed. So this kind of goes to show, as you hear later, the air brakes are engineered to slow the velocity, but also lower our altitude. And we were able to achieve this based off of our initial design. Looking forward with the future of Project DEIMOS' launch vehicle,
we look to build finally our aluminum launch vehicle. Right now, our launch vehicle prototype is made out of Bluetooth because that's what we had available. But building this aluminum launch vehicle is going to be a big step forward, especially for the launch vehicle team. We're also looking into supersonic research as we get faster and faster with our motors, and we get bigger and better. So looking into how the fins, the Nosecone, the Airbrakes, how that all comes together and affects, has different effects under supersonic speeds is going to be very interesting. We're also looking to expand it to potentially being multi-stage, a multi-stage rocket that can reach high altitudes to support different types of mission sets. And then finally, one of my personal goals is to focus on more tactical assembly and launch. Right now, the assembly for the rocket and the launch process itself is lengthy, and with different mission sets that look at maybe a tactical focus that where a soldier may be carrying something like this in the field, we want to be able to build a launch vehicle that is easily assembled and easy to launch so that when the time comes where they may need to protect themselves, they can do so pretty easily. So I'm gonna pass it off to the Nosecone team and that Olivia Jones.
We've got time to ask you airbrake questions. So if anybody has any questions specifically for Team Airbrake.
Or launch vehicle.
Launch vehicle, excuse me, sorry.
Yes, sir.
Yeah, so I have a question about the choice of aluminum. You talk a lot about thermal properties and it's some assumptions about mostly about how the aluminum is going to expand. But you didn't mention at all about where the heating is going to be applied and how that's going to affect the expansion. Did you do any simulations that talk about where that's going to be the biggest issue?
But that's something that Ali mentioned. Yeah, based off like what we did, we basically just like calculated and determined like the power and that actually how much we expand the aluminum, which was our main focus, especially with like the way that, as you said, behaves under high temperatures. But we did not like find like the source and where the heat coming up.
I would say it's when looking at aluminum, the first things that we came to mind when deciding for aluminum was kind of more of that tactical focus again. With Bluetooth, we saw the downsides being if a soldier were to put it on his ruck and he did a ruck flop, that thing's going to get crushed. Or say if it's raining, the Bluetooth is going to get soaked, and Bluetooth itself with different types of with different types of like atmospheric conditions can expand and contract. So we ruled Bluetooth out for this process, and then for fiberglass, one of our main worries was that it would shatter pretty easily. Again, like going back to the ruck flop thing. So we just saw aluminum as more, especially if used in a tactical environment, something that's going to be a lot more robust and useful just carrying around as opposed to the other two materials. It's kind of the biggest take.
Also, in terms of thermal properties, going back to the slide, we talked about, well, I didn't really talk about it, but it has a lower specific heat but a higher thermal conductivity, so it will have more of like a uniform distribution of heat, which we don't see as much with materials such as fiberglass. All right, Then to continue, I'm Olivia Jones. I'll begin briefing to you on Nosecone. The subsystem of the Nosecone is it's up to carry onto your payload. They can carry camera systems, onboard sensing systems. The payload team was transformed to Nosecone this semester and this past year. The payload team in the past has built plenty of internal systems that accomplish our mission overall, as the two was no different. The payload team transformed to the Nosecone team at the mission of enabling our overall system. And we needed to transform the way we approach problems here to integrate with the overall Dosimetry's team and accomplish the complete mission. The primary things that we need to consider this year was the environment that our system will be placed in. We will be experiencing speeds up to Mach 2 based off of our mission set. Because the system is moving at such high speeds to enable our active dynamics mission, we need to have a nose cone that can complete this need, be able to withstand these conditions, and be strong enough, simple enough, lightweight enough, and of attractive materials, shape, and able to carry our off-road payload. We fabricated our nose cone to minimize drag at high subsonic and supersonic speeds. These are the Mach 1.2 to Mach 2 speeds we're anticipating, and it needs to be custom built with the capabilities we have here at Westline, and able to carry our onboard nose cone and some of the payloads. So we're strongly limited by the materials that we have here, and had to adjust all of the capabilities based on systems. We did a large amount of materials and construction analysis to determine what we do have here available and what is possible for our system. We landed on 6061 aluminum, and this is, to note, this is the analysis done specifically for the nose cone. Launch vehicle and other systems have done similar research, but theirs is unique to their unique mission sets and subsets. We realized that we need to have a clear sleeve and an optical clear material for our camera to be able to see out of. That way, when our camera is picking up seeing all the data that we need, it's able to see where our rocket is going. And as the nose cone is picking up data, able to take this camera data and understand where the rocket is going and its trajectory path, it can take in that information, find an aerial target, and route in that direction. So it's incredibly important that we have a clear section of the nose cone that our camera can see out of with enough optical clarity so that we can fully understand what it's seeing and what it's able to do. We landed on polymethyl methacrylate for this need. We looked through plenty of plastic materials and other fiberglass options, but this was the most strong, the most non-pliable that would keep its shape and perform due to the stresses that we other. And it would be the most optimal clear, and this also be able to be something. Then aluminum 6061 is an incredibly useful material for our team overall. This is something that we, through our analysis, realized will work perfectly for the nose cone, but it's also something we can use to establish materials continuity across the entire team. Each of our subteams can use this material, and we'll be able to simplify our materials ordering process, our manufacturing process, and the integration of all of our subsystems together to form the full payback and simplify significantly by using the same material. I'll now pass it up to Cadet Halford to read to you right here.
I'm Cadet Halford. So a key component to our nose cone was the integration of cameras. Visual sensing data is absolutely necessary for active guidance, and so that was my role this semester, was integrating cameras within the nose cone. So one of the key components is the PMMA transparency. So that's a plexiglass type material that is in one of the pieces of the nose cone that allows the camera to be integrated internally within the nose cone. So rather than mounting it externally where drag forces would be applied and slow down the rocket immensely, it can be internally mounted, which allows for two cameras in 360 visual data. So the camera connects to the computer through a system on module communication, which then connects to a computer back. Cadet Avalar.
It's actually Cadet use and thinking. So we selected the von Karman Agave nose cone because it minimizes wave drag. At high subsonic and supersonic speeds, wave drag becomes most prominent drag force to be mitigated. This occurs because at supersonic speeds or Mach 2 that we're traveling at, air is being compressed so suddenly that shock waves form, and these shock waves take away a lot of energy from our rocket. Von Karman nose cone shape is determined by the Hack series equations, and basically we're just changing the C value curvature of the nose cone to minimize the drag force. Von Karman equation is able to evenly distribute cross-sectional areas of along the whole section of the nose cone, and this helps us to optimize the pressure changes across the nose cone and minimize the drag force. Especially for this semester, one key task for Ares was to take some measurements on the effectiveness of our air brakes to minimize the interference that other drag forces create and measure the drag forces that the air brakes create
wanted to minimize the overall drag force that our nose cone.
All right, so with the geometry established, the big thing here at Aries is that we're making everything in-house. So with our nose cone established, the design established, we had to come up with a way to actually manufacture it. And we talked a lot about choosing aluminum versus other materials. Now we have to figure out a way to manufacture this aluminum to a nose cone shape. So a big constraint we had working in Bartlett is that the equipment we have here cannot manufacture a 15-inch piece of aluminum all at once into a nose cone. This is because to actually cut the cone in, like you'd have to have a long enough bit to reach inside the nose cone. And the materials and equipment we have here, it's not possible to do so. So what we ended up doing is we split up the nose cone into multiple pieces and essentially Lego piece constructed them together through locking tapers. And those are what those two equations there are for. Essentially, the kinetic friction of the tapers is low enough to where you are able to basically put them together. But once they're in, the static friction holds them according to a decided upon holding force. With that decided upon holding force, we were able to calculate the length of the taper according to the type of material we're using. In that, we were able to manufacture a CAD design to actually go and mill or 3D print a working nose cone prototype. And as you can see here, that's the prototype we came up with, and we were able to actually 3D print this. The next step, which will happen next semester, is actually manufacturing it out of aluminum and also incorporating the transparent panel, which essentially overlaps over the taper to allow for camera access to the prototype. I'll now pass it off to Avionics recovery for some questions first.
Questions first. So I have a question. You mentioned doing 3D printing to prototype the pieces that you put together. Did you learn anything in that prototyping of that you're going to apply to that you use when you build it in aluminum? So now you're going to save the process because you learned something out of the 3D.
So for 3D printing, it's a different material. And because the taper length was calculated based on material properties, when we're making it out of aluminum, we're gonna have to redesign it. This is because the different friction coefficients between the two materials are completely different. And also because when you're 3D printing something, it's not gonna exactly match up with the design you model in CAD, right? This is because when you're 3D printing, it's inaccurate, it can't do perfect geometries, and also because the filament expands. So when we're machining, since it's a process of removal versus additive, we may be able to get more precise with that. And so that would also be a consideration when we're calculating the amount of holding force we want, something like that. And I guess this also just really proved that what we're trying to do is possible. Because we were able to prototype it, we were able to launch this in an actual rocket and determine that, yes, the design of having locking tapers will work and it won't fall apart like mid-launch or when it hits the ground or something like that. So yeah, yes, sir.
Sorry, I didn't mean to cut you off. Was there like a minimum length that tip had to be in order to provide enough shadow for the rest of your pieces to not, the fact that it's segmented to not incorporate additional drag into your system?
So when you say length, you mean like
like the black part.
Tip.
That's right, the tip. Did that have to be a certain length in order for the rest of the system to kind of work as one cohesive piece according to your simulations as opposed to?
So the way I designed it is that there's an outside part. This is about 3 inches here, but the taper actually extends from the first part. So even though this is such a small piece, all that had to change was that this internal taper is a lot longer on the inside. Essentially, it's 3 inches on the outside, but in reality, the piece that will be carved will be a lot bigger. So because it is smaller, the taper does have to be longer, whereas like taper down here is only about half an inch. This one's about maybe 2 inches.
The sort of clear material we're talking about, what are you going to use? Like, how are you going to manufacture that clear material?
We're going to resin print. So there are a few new 3D printers that currently the mechanical engineering department has, and the paint department is working on acquiring, where it prints in resin. And one of the other challenges we had was that if you carve something and you machine something and it's made the cylinder, you're going to lose that optic. area, they'll be all stuck on that side. So we're gonna print in resin and then heat it and cure it and rinse it in a specific process so that it maintains it off.
Where is it gonna sit on the nose cone? Gonna be the,
So we will do one of these, we'll have the internal skeletal structure and it'll fit right over the top, almost like a rail system, but it'll fit together with the tapers. We'll have a sleeve of the resin.
So the resin won't take in the structural, it'll be more just like a casing.
Yeah.
So in that case, having to do maybe the do with Lego pieces of the nose is actually a feature, not a bug. So let's say contractor picks this up and he already makes their program of record and making a lot of these things. That that's going to still be segmented. I think that we
The bigger you get in like making individual pieces, the more expensive your equipment is. So it could reduce cost if it's more modular and if it's not. You could make you could have one machine doing just this part versus one machine doing the whole thing. You could expand it across the material or the machines, so the production can increase. Or I guess you could, if you had the equipment, you could just make it in one big piece, but that comes with different expenses.
Thanks very much. Avionics.
Hello, everyone. I'm Cadet Sanders. Unfortunately, Cadet Wong could not be here today, but I will be briefing the avionics and recovery. So just for our mission statement, bottom line up front is that we have to recover our rocket in order to get the best data possible for us to be able to analyze how our launches went, what went wrong, what went right, and that is our job as avionics and recovery to make sure that the rocket that goes up comes down all in hopefully one piece, because a rocket that exploded in a million pieces can't exactly give us the most information that we could use to improve. So here is our black powder equations. I apologize. These are the energetics used for the ejection charges. And for our parachutes, we will be using a 16-inch and a 36-inch parachute in order for us to be able to recover the rocket. These are our components. So it's there, right? This is the avionics bay there on the left. This was created in-house, I believe, 3D printed. And that is a recent design, which you can see, I believe, right here. I apologize. But yeah, that is the avionics bay that we created. Currently, we are using an Altus Telemetrum flight computer for now. However, in phase 2 in the future, we will be designing our own flight computer in-house with our own code in order to get a quicker relay between the rocket going up for the apogee calculation and the computer on the ground as well. Well, short, this is that was avionics and recovery. Are there any questions? Pass it off to.
Oh, well, I can't just. Or you think there are?
So when designing an avionics bay, there's really only two methods. There's pre-printing or using the same design, the same material that you're building with and kind of making it an inner tube of sorts of the same design. For the prototype, we 3D printed so that we can fit the components inside to the liking that we had. So originally we had a pre-manufactured tube that fit within there, and it could hold one of our flight computers, but with our own design 3D printing, we have the redundancy to put both, or we could put both computers in so we could have a redundancy of having two computers. So designing our own kind of allowed us to have that redundancy, have more space, really just build out something better. Yes, sir.
Yeah, so I had a question about the avionics design. If you design the next avionics package or so, is there any limitations based on the amount of G forces from the launch acceleration on the avionics package?
Right now, the off-the-shelf flight computer we use, it takes, they use this off-the-shelf computer in super high powered rocketry for like the guys that the von Karman line. So right now, the one off the shelf we have is gonna do the trick, but our goal with the next design, avionics components that Jack is gonna design is going to take that into account, that would, withstand those forces at its higher altitude and higher power.
And do you know how many Gs you're gonna have?
Not exactly yet, but that's something we're working for sure. Awesome.
Afternoon, everyone. Them after being this snowball, we'll break down our airbrake design and how the airbrake worked for this year. So the goal this year for our airbrakes was to just be able to reduce the apogee of our rocket. So let's say if our apogee was 5,500 feet, our goal was to create an airbrakes system that could reduce from 3,500 feet to maybe 3,000 feet just by being fully deployed. And so in the broader aspect of the airbrake design, right, we're trying to find a drone and take out that enemy capability. So the airbrakes would be actuated using servos and elbows, and we could deploy those airbrakes. So utilizing the technology in the Nosecone to find that drone in space and utilizing the map done by the computers. What's being done with airbrakes in our find side act coding system is that it's determining what kind of force does our airbrake system need to create so that the maneuverability of our rocket can be adapted so that it meets that drone that's somewhere in space. And so, like I said earlier, the airbrake design is made up into 4 airbrakes. So each airbrake has a shaft and a servo next to it. So each airbrake can be actuated individually. And so that allows us to be able to enhance maneuverability of our rocket so that we can go and do an escape from bigger drone that's somewhere in space. I'll pass off to Justin to go over our solution.
Ladies and gentlemen, my name is Cadet Justin Zedwall. I dealt mainly and specifically with the simulation software. In order to prove proof of concept, we ran a multitude of simulations that kind of proved design considerations, and ultimately led to the product we have on the table. In the top left, to begin, we kind of tested our material and the static pressure that would be imposed on the airbrake system. From there, we got a factor of safety extremely high. So we know that the material that we are using can withstand the forces on the airbrake and be able to actually create that slowing down effect that we need without compromising the integrity of the rocket. In the middle, we did a differential deployment within ANSYS, where we only had a singular airbrake deployed to be able to find out what kind of momentum or moment or how many newtons of drag that singular airbrake would produce on the rocket. From there, we were able to find 6.29 newtons of drag, or about a 0.278 millimeter moment, which would be plenty enough to be able to actually turn the rocket in air pretty significantly. If we were to operate 2 or more of those at a time, you can understand that you can pretty much vector the rocket anywhere we want to while in flight. In the bottom, some other design considerations would be how the airbrake itself interacts with the fins. You can probably assume that it made some sort of turbulence whenever air is wrapped around the airbrake, but how that specifically interacts with the fin can, whether it needs to be somewhat offset from the rocket or whether it needs to be in line with the fin can itself. From there, using ANSYS, we were able to determine that no offset from the fins actually created a stronger amount of kinetic turbulence than to be in line with the fins itself. Other simulation software, or using more simulation software, we were able to find the static pressure specifically and identified high stagnation regions on the leading edge of the fins, as well as our fluid field visualization, which used velocity path lines to be able to determine the turbulence on the rocket itself. From there, we are able to see that most of the flow across the rocket remains attached. It's a really good sign. It shows that there is no turbulence or crazy vortices that come from the rocket and the airbrake system. And we can maintain stable flight, even with the airbrakes fully deployed. And all of these simulations were done with the airbrakes fully deployed. And then this just ties into Bernoulli's principle that as you have higher pressure, you're going to expect lower velocity, and with higher velocity, there will be lower pressure. And that ties in, it just proves that the rocket itself follows the aerodynamic forces we expect to see on the flight profile when we fly it for the first time as a full working prototype.
So just a few weeks ago, we were able to actually conduct subscale launch with our airbrakes being fully deployed. Like I said earlier, the mission is to create an airbrakes system that can reduce the apogee of the rocket, as well as like determine the actual drag that's created by those airbrakes. So through just in simulations, the airbrakes alone came up with a drag coefficient of 0.6. But from our subscale launch, we learned that not just the airbrakes, but the entire rocket itself has a drag coefficient of 3.27, and it actually reduced the apogee of the rocket by 30%. So this is a great sign, and for the airbrakes team, like we consider this a success for the year because we met our goal of creating an airbrake system that can reduce the apogee of the rocket. So that means going forward, we do have potential to keep iterating through our airbrake system so that we can then control the rocket with these airbrakes. So create and enhance the maneuverability of this rocket so that when it does find and detect a drone or a UAS capability, that we're able to neutralize that. Ladies and gentlemen, that concludes our brief. Any further questions?
So you did a simulation without air brakes and you did an actual with air brakes. Did you do a simulation with air brakes to compare what you did out of the range to what you simulated to see how they compare?
Yes, sir. We got the
simulation with air brakes.
We did, all of the simulations were run with air brakes or with a partial air brake deployed or with no air brakes deployed. So the ones kind of depicted on here, like this is with air brakes fully deployed, you can tell with the turbulence that is created and then it shoots back.
Okay.
And then on the left is with the air brakes fully deployed, but the air brakes singled out. And then on the first slide, a singular air brake deployed in the middle, the bottom, all 4 air brakes deployed, and then on the top, the air brakes deployed.
some of the reason behind like testing one airbrake deployed versus bottom is that in the future, you want to see, okay, maybe to take this steep or part of a left turn, maybe we want to deploy one airbrake or 2 airbrakes. That was the reason.
Sir, to further that question, the launch simulations that I use for the launch vehicle were with air brakes retracted, mainly because the software that I use does not have like air brakes as an option. So we use the simulation data for a launch without air brakes to kind of give us another set of data that we can compare the air brakes launch to. And the reason behind that is because we were going to do 2 launches, one without and one with air brakes, but we ran into a time constraint where we could only launch one time with air brakes deployed, so we could compare simulated data to the real. So it's a perfect question. It's
Did you find out that your rocket, like that the rocket was like controllable, like using the 1 air brake or 2 air brake? Like were you able to like change its course or like change its trajectory, like through integration with it?
With the data from the subscale launch, we can, not definitively, but I think we can assume that deploying 1 air brake instead of all 4 would definitely change the direction of the rocket, but controllability is like what next year and definitely years after that, like we need to figure out like how much do we need to deploy a single air brake versus 2 or 3 to like have it control.
Turbulent air. I know you guys talked about that. I'm very interested. If it's in turbulent air, it's an air brake, that's going to be the overall system of the rocket.
Yes, ma'am. So we're playing with different locations of the air brake. So as they are right now, we can see that the air brakes would disrupt the flow over the fin. So what the air brakes give us are 2 axes of controllability, replication or yaw, and our fins give us the roll stability. So in this current configuration, these air brakes would actually take away our roll stability, which gives us less controllable rockets. So future iterations of this research see the air brakes taking place at the center of pressure, possibly being farther back in between the fins so that you're not disrupting the flow. You still have that 3 axes though.
And to add on to that, and we're also looking to add certain canards help adjust flow as well.
Thanks. Thank you very much. Any other questions?
All right, I am Cadet Unit. I'm Cadet Wilson.
Cadet Bauer.
And this is the design and tactical study of a man-portable high-energy laser for counter-unmanned aerial systems. And this is Lucas, the laser unit for counter-aerial suppression. Awesome. All right. So what we noticed is there's a big capability gap in our wars. So we're seeing a lot of drones being used, especially Iran, Syria,
and Ukraine, and we don't have a good capability on the platoon and squad level to take them out. So what we've got the DEIMOS, which is a striker platform, which is great, but you need to be in one of the upper echelons, like battalion-sized element, to have access to these. It's not going to work for a discipline. We've got shotguns, which have their benefits, but at the same time, they've got range issues and accuracy. You got to be able to lead your target, which is difficult. And then finally, we've got, in addition to that, there's multi-projectile rifle rounds, less common, still used. Essentially, you're making a shotgun out of a rifle. And then we have the drone busters, which are going to use your radio frequency to confuse drones, the same way that they're getting their input from their controller. The problem now, as we're seeing a lot in Ukraine, is we got fiber optic drones that are getting that feed through the cable, so they don't rely on the radio signal. So they can't be disabled by these drone busters. So primarily we're targeting these group 1 and 2 drones. They're inexpensive to produce, and there's a lot of them. Pass it off to Jonathan.
All right. So with designing it, we need to consider the size, weight, and then the power that we're actually going to be involved with it. So that's why we made the technical decision that we did. So for the size, we want to be able to fit on a rucksack, so we can put it on dismounted patrols, so that we could be able to counter it in the field. We wanted the weight to be able to be carried by one person, so you didn't need a squad size element to be able to move it. And then the power to be able to take down the drone. And then with that, we wanted to also be able to include junior enlisted operators, so that you can be able to hand it to your everyday Joe. And then with very little teaching, they're able to still be able to operate the weapon, which is why we modeled it off of an M4 platform. We want to be able to easy maintenance, so in case anything breaks, a screwdriver, you can just replace whatever's broken. And then also be able to, for it so it's safe, so that we have electronic and mechanical safeties. So with this, our components ended up, we have our 400 watt solid state laser. That's a IPG photonics. It comes from a welding laser. We then have our e-bike battery. That's a 48 volt with a 14 amp hours, so it has about 40 minutes of runtime. So think about going cyclic for 40 minutes on 2-volt output. It's a little overkill. And then we also have our buck boost converter, which basically lets the laser and the battery be able to feed into the actual laser itself, which then feeds through fiber optic cables into the actual laser collimator itself, which then is based off of our weapon, which is a designed off of an AR-15 in an M4 platform.
So when we're looking at building this, biggest thing is mobility. So it's got to be rucksack based, and it's very heavy right now. That's one of the things we're going to work on in the next semester. Right now, that is about 75 pounds. So I weighed in at this morning. We're gonna get that down. The wood case was just for prototyping purposes. It needs to be cost effective. Right now, a lot of our options are pretty expensive to shoot stuff down. So all of these are commercial off-the-shelf components or produced in-house, and ammunition is charging the battery. And then accuracy, you're working with a light speed projectile, so there's no bullet drop, and it's longer range than conventional options, and you don't have to get any because it's light speed.
So last week we went out to the range to test this for the first time in the outdoors. Our two main goals: number one, we wanted to see how it performed in a realistic setting, so not just in the nice lab. And then secondly, we wanted to see how well a human could do with this. So it's a directed energy weapon. You have to hold it on target for a specific amount of time to get through the material you're trying to break through. And how well can a human hold on? So in our operation here, we treat it as a crew served weapon. So we have in the prone here our weapon handler. They're strictly aiming the weapon.
they're keeping it downrange the entire time. We have the laptop operator who is acting as the trigger mechanism, and they can control that via the laptop that's connected into our laser box. And then finally, we have our RSO, who is acting as the safety, as in the safety on your M4, and then also has the viewer to see the IR beam to ensure that it goes on and off correct.
So what we're actually able to do with the range, the sort of results we got from those goals he laid out. One, laser needs a lot of time on target. So if you see that picture sort of in the middle, those are 2 1.5 piece of plywood, and those took about 1 minute and 16 seconds to burn completely through 50 meters with full power, so 400 watts. So that's significant time on target. We do think that time is going to go down with more drone-like materials. Obviously, drones aren't typically made out of wood. I think the plastics in a drone are going to be a lot shorter time because you're melting, not burning. So that's something we're going to look into next year. And then human ability to remain still, that's going to reduce your effectiveness quite a bit. So the picture on the right, that is a 20-second burn of a human operated shot. And that's about 4 inches by 5 inches of burn that you see there, just in the normal breathing pattern. When you shoot an M4, you squeeze the trigger. As soon as the bullet leaves the barrel, you can move again. But with this, you're staying on the target for significantly longer, and it's going to move as you breathe. So that's something we need to address and continue to work on to make better. And this is so you'll see it pop up here, right there. So your phone camera actually has a little bit of IR spectrum in the camera. So the human eye can't see that, but your phone camera can. So you can see how much the beam is bouncing around on that target there. So it's quite a lot of movement for what we want. So we're going to try and reduce that as best we can in the future.
So our next steps for this project, we want to make this fully like field ready and capable. So contain all this into an actual case so that it's weather resistant and like battle hardened, so you can take it into the field and not have to worry about it. So it's not a liability. And then also contain our weapon system so that you're able to, it's pretty rugged. With that too, we also want to add in an actual trigger assembly instead of just running off a laptop, so that this will be a fully self-contained system. With that, we'll have a very variable output, power output, and then also have a data screen that'll show that variable output. And then we'll also include mechanical and electronic safeties with it. And then we're also hoping to include a IR optic in the top of it, so you're actually be able to see point of impact. So you basically have like unlimited tracer rounds, essentially. So you can actually see where you're shooting, which will hopefully improve accuracy. And then we're also going to optimize the rug frame to decrease weight and just throw in the field more into all the solutions. And then, so with that, so our project impact for our goals of this is we want an accurate, lethal, mobile, and cost-effective solution for taking down drones. So our end state is a directed energy weapon that can be used by one person for a dismounted unit to take down class 1 and class 2 drones for a platoon and squad system.
This concludes our brief. Any questions?
Is there any plan to add something like almost like a camera stabilizer to the end of the mounts to keep that human error to minimize?
That's one of the things we're looking at. That's probably a next semester project, is looking at how to stabilize that beam.
Yeah, any ways to just like increase the accuracy on it is, so hopefully you can see where you're actually shooting at. And then also, if you can also, like any other systems that will help improve clarity and like stability on art, we're looking to really including anything. That also doesn't restrict weight too. You still want to keep it light enough that a person can carry it. We're not trying to knock it out.
Yeah, another way you could improve the accuracy is to not use a continuous wave. Have you looked or thought about using much higher power but much shorter duration pulsed lasing?
So, the problem that we run into when we have, stronger power is you need, a higher, a more powerful laser to do so. With that though, increases, the size and weight, and also the power for it too. You need a much bigger cooling system to be able to run that laser. So we start to, include in a lot of the systems, that just makes it a lot harder for a person to carry it, and it starts to turn from a person carrying it to like a monkey carrying it. But the pulsing effect we are looking for the increased durations, the shorter wavelengths, the higher the impact of it.
Eric, talk about your AID this for you and Brandon.
Yeah, so actually me and Brandon are actually going to Huntsville, Alabama, this summer to work at the Red Star Arsenal to work on pulsing laser effects on the nanosecond scale. So to see the impacts, the material impacts of those short bursts, and then how that causes for the degradation of the material with those short bursts and how it affects it.
Hopefully we'll come back with some knowledge, maybe incorporate it a little bit more.
Your prior service help understanding what a platoon capabilities are and levels of using systems?
It definitely included how much I don't want to carry around which like its own system though, but then on it too is like how much you need to like incorporate it into the actual squad size helmet. And then also like the usefulness of this can be in it. So we've also been talking with like Major Parker has other contacts that are like overseas, and they are like starting to now actually start to deal with the drone issue. And so they're trying to rapidly come up with these effects of it. We'll let them know that we have a backpack or laser, and they want to know when they can use it. So seeing the actual like the purpose of it, and then like the actual like implications this can make just outside of is this possible, definitely makes it so that we can start talking to those people to see how we can implicate this better and how we can make this more useful for the squad.
There's plenty of time to iterate and reviews. Exciting. Thank you, Jess.
My name's Jason Merriam. Today I'm happy to speak to you. My research focusing on laser propagation and Rotorcraft-Induced net fields. So the purpose of this project is to understand really if you are to incorporate directed energy laser systems onto aircraft, rotorcraft, and other aircraft as well, how the propagation of that beam through that cloak field will affect the intensity distribution of the beam on a certain target. Now, this is important to the Army because the Army is looking at developing specific aerial platforms that incorporate directed energy systems. So to support this work, we coordinated with Army Development Command researchers in Montreal, California. Actually went to go see their facilities and how they went on testing as well. What they were able to provide us was three-dimensional computational fluid dynamics data sets that we can analyze the density distribution, density gradients, as well as the vorticity structure of the waves as well. The research goals mainly is to understand how the intensity is redistributed once it reaches that target point. Additionally, want to inform future aviators how to avoid certain flight profiles, maximize the output of that energy. So this is an example. You'll note that this is a static plot, not a time-dependent flow field, which is important because computationally, just a single three-dimensional density plot is many gigabytes of data. In order to propagate the laser beam through such a field, it's a lot of computation. One of the things we're looking at back here is incorporating the time-dependent flow fields, which will require a supercomputer. But a few initial points to go over here that these dark blue portions of the field represent areas of higher vorticity. correspond to areas for density. The red cylinder there is propagation of the laser beam through the flow field. And what's important to note that we did is we propagated from the top of the field to the bottom of the beam, specifically to analyze how that intensity distribution changes when it interacts with areas of higher vorticity compared to lower down the field with those weaker wave structures. Let's see, the same thing here. Just pay attention as we go through the different plots. That is what all these plots are based on. Intensity distribution and such. In order to do this computationally, we have to break the field into a bunch of smaller slices as we propagate, which leads me to my next point. This is an example vortex. Now, it is exaggerated for the purpose of understanding how the beam travels through this vortex and where the beam ends up on the other side. Now, what happens is when the beam interacts with certain portions of the wake, it's going to refract in certain directions because the density gradient is different from outside the vortex compared to inside the vortex. I'm sure some of you remember from basic physics that what's changing is density, which correlates to a change in index of refraction, which is what refracts the beam inside of the vortex itself. There's a lot of math here, but the key points to understand is that the first point of converting density to an index of refraction change. You can think of the field as an index of refraction field where we propagate through it and different wavelets incur different phase distortions and phase delays. That when they recombine and we propagate on the next slice, what you're seeing is a phase accumulation as we propagate through the entire field. There are some Fourier transforms that are performed to take it from positional space to transverse frequency and then back to positional space so that we can create an intensity distribution of that data and visualize it. Two important points to note here, and one way we are able to quantify this is through something called the Strel ratio. Now, the Strel ratio is used in astronomy topics and modern optics as well to compare the ideal beam with the aberrated beam that flows through the, or that propagates through the flow field. So notice as this animation plays that the Strel ratio is slowly decreasing as we propagate through the field. That's because there are phase delays that are being incurred as they interact with those wave structures. You'll also notice that the troughs in air density directly correspond to the helical structure flow field, which are the vortexes themselves. Now you'll see that the Strel ratio kind of oscillates back and forth. Once again, that is because of the helical nature of the rotating rotor blades producing those vortices that hurl down underneath the rotorcraft. Another important point, another final plot here for our results is an intensity distribution as we propagate from higher in the wave to lower in the wave. You'll see that the intensity plot, the beam actually oscillates vertically as well as laterally because, once again, it's interacting with those wave structures in the flow field and reducing the intensity as it does so. Another point that is important to pay attention to is the intensity cross sections. The beam is propagating Y direction, which means that it will have intensity components in the X, Z direction. So just watch as the animation plays that the beam will wander laterally as well as vertically. This is important for the operational considerations that I'll talk about. Play one more time so you can see the real effect. You can see the intensity coming back once it propagates through the lower portion of the field. Again, because it's interacting with those parabol wave structures. Lastly, operational considerations and why does this matter to the Army? Once again, the Army has been very invested, very vocal about its interest in incorporating directed energy systems into modern platforms. They've done so strikers, striker brigade combat teams. So how do we incorporate this into modern aviation and thermal technologies? Because there's a high risk, as we've seen in the Russia-Ukraine war, where Ukraine has used
small, Crane and Russia both use small drones with munitions on them to take down multi-million-dollar photograph systems. So that is a key component. There are many considerations when talking about these flow fields. For example, when incorporating tail rotors into the equation, we know that the blades themselves are shorter, they're thicker, they create stronger vortices, approximately 3 times as strong as a Chinook. So that is very important to understand when you're looking at, when the Army is looking at incorporating directed energy systems onto these aerial platforms. The path forward for us next semester is to look at, as I discussed in the initial slide, is time-dependent flow fields, which does require a supercomputer because each of these individual 3-dimensional plots is tens of gigabytes of data. So in order to do that realistically, is keep it at a certain elevation, as if it were mounted on the aircraft, we would need time-dependent flow fields to more accurately model the situation. Also, we can perform rotational and angular analysis. So as opposed to directly propagating through the center of the field, we can propagate at different angles or vertically as well. Finally, we also conduct experimental rotorcraft testing, which in order to save the Army money, instead of trying to incorporate it directly onto an aerial platform immediately, which takes a lot of technical expertise, my advice would be to deploy it on the ground first. So have a ground-based laser system and a rotorcraft where if you're looking at since the Army is looking at developing the V-280 Valor utility rotor aircraft, you want to put a directed energy system on that, you have to understand how it propagates through one of those fields will wait for so. Any questions, references?
Very nice. So I had a question about, given that the 3D density fields are very, very large, and like I said, going to the time dependent, you need to move to much more higher performance computing. I was wondering if you've looked at using the current data sets where you have a static weight, but looking at like an averaging effect where you're propagating through many, many random directions to see the average spread and deviation and diffusion of the beam by propagating it many times through that same individual data set.
Yes, sir, that is a great point. And we can do that. Specifically, just with this semester, we focused on understanding the entire field initially. And if you're going to employ this to a specific aircraft, that is when you go into, okay, what elevation below the rotor plane am I actually going to want to incorporate this directed energy system? So that's where we can incorporate, okay, now we can propagate through different slices laterally above that flow field. So that's the next step.
Legal, yes, is it DEIMOS?
Yes, last names.
Don't be directly here. They can do solutions for HPC for us out there.
And their problem is that they have the aerodynamics down very well, but the laser propagation part comes from the photonics research. So that's where our expertise in lasers meets their expertise in aerodynamics.
We can get Army based HPC. Any other questions, James?
So again, I'm Ben Flossie, this is going to Merit. We're talking about assessing concrete after treatments from high energy conditions. So quick agenda, we're going to get an introduction, talk about the theory, why this all happens. We're going to talk how we actually did this process, and then what we found from it in future configurations. So the introduction. Why is this important? Across all military forces, we are trying to introduce these direct energy weapons. And there's two things that we have to worry about: collateral damage and actual degradation using weapons. So collateral damage. On these high energy laser platforms, light can bounce, can reflect off of many surfaces, or we can miss. And what will happen if that happens? What happens when we hit concrete a little off to the right of the laser platform? What is going to happen to the buildings around it? So first that, and then also degradation. What we're actually trying to do. We're going to engage this concrete and see what we can do to prepare the concrete for later kinetic action. So I'm going to hand this over to Brad for theory and production.
So a quick overview of what we're trying to achieve. So there is already existing high temperature effect research on concrete, mostly uniform heating using furnaces. They usually test it for some sort of fire hazards against most concrete production, but we're obviously using a laser. So some of the high temperature effects of concrete, there's three main effects caused by heat: moisture loss and mechanical strain. It's not limited to thermal expansion alone. It's also limited to things like the load that is bearing. It creates actual deformations within the concrete, and all of those create strain that is caused from the creep that impacts the different strengths that the concrete now possesses. Obviously, with lasers, we're going to have a higher temperature gradient, but we're still going to try, as we will show later, to keep a constant heat effect for a variable amount of time. So moisture loss and internal damage. To explain all this, we strike our concrete with a laser, and the concrete, which is aggregates and it has moisture content, the moisture is going to rapidly evaporate from the laser heat. And once it evaporates, it wants to escape. It wants to escape from the internal of the concrete, which creates weak integrity issues inside as it pushes the aggregate outward. This creates an internal pressure within the concrete, and it creates vacuums within the concrete as well, both that expand the concrete out, but as the water escapes, the concrete is now more brittle and dry, and it will shrink. And if there is no load bearing on the concrete, that expansion is going to go unopposed, and it is going to leave our concrete brittle. It's going to create microfractures, and that's what we're hoping to achieve in order to decrease its strength. So a lot of the theory that we went into is kind of revolving around multiple articles from places like Oak Ridge primarily that go deep into uniform heating of concrete and what it results with loss of compressive strength. So as I mentioned earlier, there's a couple of spots. It depends on temperature, pore pressure, and strain. And the total concrete strain is just a difference between the free thermal strain and load-induced thermal strain. In the future, we'll focus on more load-induced thermal strains, but we wanted to see first initially just results of our concrete degrading. So all of our samples that we've currently undergone have been unstressed concrete, meaning that we'll see, because we'll get more noticeable results as there's no load that is pushing those aggregates back within the internal structure of the concrete. These graphs show just simply the coupling effect on the right side, which is that creep and shrinkage simultaneously through heating is going to be optimizing the deformation potential within the concrete. And then on the left, you see that the compressive strength of a specific ACI 216 under a time-dependent temperature, you see that the residual percentage of the compressive strength is going down. This final one I thought was really useful. It shows multiple different average reviews and testing that use multiple different types of concrete ratios. And you can see a trend line downwards as the temperature increases of the residual compressive strength. So I'll get into some of our experimental processes now with Aaron.
All right, so first off, let's talk about the laser that is actually used. We have a 1.5 kilowatt laser that is an IR wavelength spectrum at 1070 nanometers. It has a 2 centimeter spot size, and it has a Gaussian beam profile. We are about 8 meters away from our targets in the lab, and it has gone up to around 25 meters out on the range. So what we've done over the last 2 years is first we started with smaller samples. This is mostly because it's very hard for us to get concrete. We actually get it from Han. They bring it over every once in a while. So the first thing we did is we cut our bigger samples into smaller ones so we could get more tests. So as you can see, we have these pretty small samples here. What we did is we hit one point right in the middle of our like circle, and it would hit it for either 10 minutes, 25 minutes, or an hour, all at 50 or 500 degrees Celsius. And then we also did one test at 600 degrees Celsius to see if there was a big difference. Then the actual compressive strength, we did a punch test. As you can see here, we got a little metal punch that was put right in the middle of the cylinder, and then the compressive strength was tested. For this year, we got a little bigger cylinders, which is great because it's more realistic, obviously. When we're actually like in the future using this system, we will be getting much bigger samples. So this year, we only did hour-long engagements. So we started with a 10-minute heating up period. They got us up to 500 degrees Celsius. We used the same 8 meters away, like laser everything, but we had the laser paint the front of the cylinder from top to bottom. So we had an equal heat gradient across the front, and then it went back through the system using. So we did a hour-long period, and because of our limits here, we couldn't really stay for more than an hour when we're actually doing it. So we let it cool for 24 hours and try to get back to it the next day, do another hour-long period of heating. For the 2 tests that we did compressive tests and tensile tests. These are the 2 tests here. Compressive, you put it vertical, you crush it. And then the tensile test is a little more different. We put a steel bar along the horizontal axis of it, and then as you crush it, the 2 sides split apart and they pull. That's why it's an actual tensile test. And now when we talk about the results,
So we went over the 2 primary tests that we've gone over so far. This one is based on the concrete discs. That was the first experimental process that we mentioned. We have this beautiful graph right here that shows about an average peak compression strength loss of 33% when we compare it to the control samples. So if you look at this graph right here, you see different colors. All you have to know is that the control is the purple one, and we're seeing a lower every single time, almost entirely based on the time that we lace each of these samples. The degrees, we couldn't go much higher than 500, 600 degrees Celsius because one of the goals initially of this research was to not leave any sort of visual mark on any of our samples. And if we went anywhere past the 600 degree range, we start to see visual signs of lazing upon our concrete. So 500, 600 was our sweet spot. And therefore, the biggest factor became time. But when we initially got to it, we found that the average treated compression peak for pounds by force of the treated samples was about 2,119 pounds of force, and our control was about 3,097 pounds of force. Here is some of the results that we got from our second test that we conducted. So first, the compressive strength, the compression strength vertically with the larger concrete sample to be achieved on average peak compression strength loss about 12.6%. What we found from these is that for the compressive strength, at least, there is a lower variability. And we believe that is because concrete, we achieve the intended purpose of removing enough moisture within the concrete to create a weak internal structure within the concrete. There's enough air holes inside these concrete cylinders that when we crush them, we basically cascaded with the inside and then pushed enough aggregate outward for the concrete to basically crush faster. The split tension, we didn't see the results that we quite wanted. We saw that the average peak compression strength was only lost by about 3.6% from the control sample. And we believe that this most likely is because concrete is already not very resistant to split tension. And because of that, if there was any basic creep that existed beforehand, before we laced any of these samples, that would be enough if it cascades to create the actual crack that's supposed to come into. Some future considerations for this project that we want to focus on
One, we want to pivot towards load-induced samples. As I mentioned earlier, load-induced thermal strain creates a very big difference in the resistance, especially compression strength of concrete, as now the aggregates are not able to expand unimposed. They are going to be able to have at least some sort of force that's pushing them back in, increasing the overall strength of the concrete. So we want to see if we can get a desirable effects from it as well. We want to try different concrete strains. We want to try different ratios to see if there's high performance concrete versus lower performance, more commercial concrete, things that we might see more commonly in different areas of the world. We want to see if those effects are similar to the ones we tested on. Longer lace periods is a given. Concrete is not a good conductor of heat, so it takes a while for the heat to diffuse. So we have to focus on having longer lace periods and more sample size, or larger sample sizes. We wanted to also focus on ballistic strength. We've had some ideas how to incorporate that. That's the main goal, as the final destination of this research is to test the ballistic strength of concrete, but it's just not very practical. And then finally, just different types of strengths, including flexural strength and better strength characterizations. That will conclude this presentation.
I'm sorry, I might have missed it, but why exactly did you not want to leave a mark?
The main reason we don't want to leave a mark in concrete is because if we are using this for any sort of yes, don't leave us. Any other questions? We can't answer something.
Would you consider as lazy concrete was under pressing strain, like do you expect?
First, that is one of our biggest goals, because that's the most unpractical, obviously. It's very hard to do, because if you're doing that, it's either in the hydraulic press, which can cause issues, or there's something huge on top of it. So it's hard to practically test and research unless we have like a building that is ready to be demolished or something. So,
Are you
you have a building that's ready to be demolished?
Talk to range people.
Are you saying the laser lasers?
Wall is under.
If we can figure out a practical way to do it, that would be the best thing that we can do.
Let's talk to range.
They're all cars are a trouble. How to deal with cold weather and get it to cure out in the right time. Use different habitats to make that happen. Guys, sometimes you can't wait till spring to make construction happen. And there is a certain quality depending on what kind of an attitude you put in. Guys don't get it all.
So this research got inspired by research coming out of the University of Houston. They took many, many different types of concrete. They put them into that furnace that we were talking about. All of the concrete was degraded. All of them got degraded. So our hypothesis is that any type of concrete would be degraded. It's that difference from concretes, like which one would be degraded more. So maybe if there's more water content inside of one, it'll be degraded better. But that's a future. If we could, if Mahat can give us different types of concrete.
Do you guys find like splinter or like cracking patterns that were like similar between like the different levels of concrete, or like the power levels between all of them?
Listen, yeah, it's just little micro fractures in the front. You can literally hold it up and just see fractures. Just they're quite small, maybe a centimeter. Yeah.
Concrete dissipate heat very well, or does it say it's not very well heated?
Basically, concrete does not conduct heat, and it will basically push into a situation where we have to just live for a long time in order to get to the interior of it. If we don't laze long enough, we are essentially only possibly getting to the very, very surface of our sample. We're not going to achieve results of shrinkage. So it will get to the internals. We've been working on measuring the amounts of time that we lace and then trying to weigh before and after the concrete to see how much of the mass was lost due to water loss. And at least on the second testing, we found about
In the region that reached 100 degrees Celsius, there's been 63% loss in water. Which is not that, if we get it all the way through the concrete, it shouldn't cause significant degradation.
Obviously, there's a certain period of time where, at least with our samples, we saw this with, especially with small discs, that you laze it long enough and it's not, the water is thin and you can't remove more water than already exists. That's not really as big of an issue when we're getting water samples, but we noticed that was.
One more question.
Yeah, so I think the thing that surprised me most about what you showed is that even to 500 and 600 degrees, concrete is amazingly robust. Truthfully, yes, it lost some strength, but it only lost 10, 15, 20% at most. I mean, we know the Romans had fantastic concrete. It's still here today. Concrete is amazing stuff. But my question is, given how robust it is and how it's not changing very much at, say, 600 or 500 centigrade, has there been research, or do you know if you're able to go to, say, 1,000 centigrade, is it nonlinear? The degradation, is it dramatically different? Do you have any idea how that goes?
We have just played around with just seeing how high we can get it. It just starts melting the concrete. It turns into like black glass. I believe the silica in it melting. So past a certain point, it's just kind of melting into it, and then that melted glass starts messing with the profile. It changes things.
Plus, then you're leaving a mark.
Exactly.
Got it.
Yeah.
Questions?
Awesome. Thank you so much, guys.
This concludes Department of Physics and Engineering Project Day. Cadets, I would ask 5 minutes to help us reset the chairs. That would be much appreciated. So thank you for coming, everybody.